And before we get started, I'd like to cover a couple of issues. Thanks for joining, everyone. We've got a great presentation, a long presentation today. But before we get started, I want to bring everyone's attention to the Exceed Code of Conduct. Everyone is generally on good behavior, but if you notice any behavior that you think is inappropriate, please, you can submit a report to exceed.org/code of conduct. And then we also try to provide training events that foster inclusion and show respect to everyone. So we try to be sensitive to terminology we use in these webinars. But if you observe any terminology that you think might be inappropriate, please let us know by sending an email to terminology@exceed.org. And so with that, I will stop sharing and hand it off to Bob Sinkovitz, who will provide an introduction. Take it away, Bob.
Hey, good morning, everybody, or yes, early afternoon for those of you on the East Coast. So we're gonna be covering the transition from Comet to Expanse today. We've got a full day of material. I'm looking at my slides and I might have a little bit too much to cover. So some of the content I'm going to go through fairly quickly. Just a quick rundown of what we have planned for the day. So I'm going to spend about a half an hour giving a general overview of the system and allocation process. That's going to be followed by Mahidar Tataneni to discussing running jobs and Expanse and some of the differences that you're going to see from Comet. Then a short break. After that, Marty Candice will get into software module environment, compilation, and optimization. Another short break. Then we're going to have a presentation by Nicole Walter on job charging and something that we call TRES, which accounts for the usage of memory, CPUs, GPUs, and comes up with a fair way of charging for those jobs.
I'm sorry, I'm not sure what's up with your screen sharing. We're only seeing the tabs of your browser.
That's not me sharing.
I am trying to share the schedule.
Yeah, something's wrong.
Oh, okay.
That's okay. I think everybody has the link to the schedule, so I'll just finish this. Then I'll be sharing my slides in just a moment. Thanks, Mary. We're going to get an overview of the Expanse Portal by Suba Shivananam, followed by Interactive Computing and Running Jupyter Notebooks and Expanse by Mary Thomas, and then a brief session on data management, in particular data transfer mechanisms, how you're going to move data to and from Expanse. And then we're going to wrap up with a short Q&A. So I'm going to go ahead and share my screen, jump into my presentation. I'm happy to take questions as we go along. Let me ask that one of the folks at SDSC, though, maybe Jeff and Mary, if you want to monitor the chat and just interrupt me if you see a good question come in.
No problem.
All right, so I'm going to go ahead and share my screen. Okay, is everybody seeing my presentation now?
Yep.
All right, good. Let me just rearrange my workspace a little bit. Okay, so my name is Bob Sinkovitz. I'm the Director of Scientific Computing Applications here at the San Diego Supercomputer Center. Again, welcome to our Comet to Expanse transition workshop. And I'll be giving you a brief overview of the Expanse system. Okay, outline for the talk. Again, we're going to start off with an introduction and overview. We're going to get into the Expanse system architecture. We're going to do a little bit of a deeper dive into the AMD EPYC processor architecture. This looks very different from the processors that we had on our previous generations of machines. Going to talk about the hardware details, NUMA, non-uniform memory access options, some of our experiences with applications. We'll then cover Expanse's innovative features, discuss the allocation process, and then wrap up with a brief summary. So the name of our award is Computing Without Boundaries, Cyber Infrastructure for the Long Tail of Science. So this machine is funded by the National Science Foundation, and we do support all academic researchers in the US. For those of you who've been computing with on Exceed resources for a while, you probably know how things work. If you need a relatively modest amount of time, you could get that pretty easily through a startup or a rapid access allocation. If you need larger amounts of time, that's done through a competitive review process. But again, for all academics, this is access to Expanse is going to be free. This is what we call a Category 1 capacity system. So these are the larger resources that are allocated through Exceed. PI is Mike Norman, who's also our director here at SDSC, Ilkay Altintash, Amit Bajumdar, Mahidar Tataneni, who you'll be hearing from later, and Sean Strandy are the other co-PIs. A lot of folks ask, how much do one of these machines cost? So it was a $10 million acquisition. So we mean $10 million for all of the hardware, and then another $2.5 million per year for the operations. So that's the systems administrators, the user support, the training, and so on. Primary vendor, who we call our integrator, is Dell for the HPC system, and Eon Computing for the storage systems. And then for the various components, the compute, the interconnect, and so on, processors are mostly AMD, but we have a little bit of Intel hardware in there on the GPU nodes. NVIDIA provided the GPUs, and Mellanox the InfiniBand network. This is the figure that we use in our proposal to kind of tie everything together. I like to describe it as computing without boundaries. It's a big system, 5 petaflops total capability. So this is about twice what we had on Comet. It's also a big data resource. On the HPC side, the machine is divided into what we call scalable units. I'll be talking about that in the next few slides. Total of 728 standard compute nodes, which doesn't sound very big, but each of these nodes has 128 cores. So there's a lot of computing packed into there. We've got 52 GPU nodes, each with 4 GPUs, and we have 4 large memory nodes, each with a capacity of 2 terabytes of data. So we have a few applications like de novo genome assembly that can really make good use of those large memory nodes. It's a data-centric architecture, and what we mean there is that the whole system is built around moving data quickly to the CPUs, to where we need to do the computing onto the GPUs. So we have a total of 12 petabytes of performance storage, a lot of bandwidth to those file systems, 140 gigabytes per second, 200,000 I/O operations per second. We've got fast local storage on each node, so we call it NVMe, not non-volatile memory. This is a great place to put files that you're going to need repeated access to, say temporary files that you're using during the course of a job. Even though it's non-volatile, the NVMe storage is going to be wiped out at the end of your job, so it's available for the next user. But if you need to work with a large number of intermediate files, even if you're doing something like writing a lot of files, tarring them up and saving them for later, the NVMe is a great place to do that. We're also going to have 7 petabytes of Ceph object storage. We have high performance research and engineering networking. I'll show that in the next couple of slides, which means that Expanse has great connectivity to the outside world. Mentioned this already, but we're supporting the long tail of science. And by long tail, we mean those users who have jobs that range anywhere from a single core, often high throughput computing, many of those small jobs, to kind of medium-sized jobs, hundreds to a few thousand processors. There are other Exceed resources available for folks who need to run at very large scale, say tens of thousands of cores, but we find that the vast majority of users fit within what we call this long tail. We've got some innovative features of Expanse that I'll get to later. Composable systems, support for high throughput computing. SDSC has always been one of the pioneers in the science gateways, and we're going to be continuing to provide great support there. We're providing more capabilities for interactive computing. We're going to be supporting containerized computing. Containers we find are really fantastic when we have users with complex software stacks. Say they need a particular version of an operating system or certain versions of low-level libraries like glibc. Containerization gives you a lot of flexibility so that you can run that container anywhere. We don't use Docker containers because of the security flaws, but we do support the singularity containers, which are great for most scientific applications. And we're also going to have cloud bursting, which allows you to submit jobs to Comet. And if you have your own cloud allocation, that you would potentially be able to burst to the cloud. So I think it's a really, really innovative feature. Okay, so the hardware, I mentioned we have 728 nodes. Each of these have 2 AMD processors, 2.25 gigahertz. Each of those have 64 cores per socket or 128 cores per node and 256 gigabytes of DDR4 memory. So this is a total of 93,000 compute cores. We also have 52 4-way GPU nodes based on NVIDIA's V100 GPU, and they're connected via NVLink. So if you have applications that run on multiple GPUs within a node, and you need to rapidly move data between those GPUs, NVLink can give you a tremendous performance boost. So we've done a lot of benchmarking on Expanse, and we expect that we're going to get better than 2x throughput over Comet. So we're seeing both a per core improvement over Comet's Intel Haswell processors, plus we have roughly 2 times the core count. And overall, we expect that it's going to be a very smooth transition from the Intel to the AMD processors. You know, our team has already compiled and run a lot of the common software packages on Expanse. So if you've been using the software that we install on Comet, you're going to see all of that same software on Expanse, the molecular dynamics and computational chemistry, various math libraries, and so forth. And we went into full production on December 7th last year, and we are slated to operate Expanse for 5 years. So getting a little bit into the Expanse system architecture, I'm not going to go too deep here. We're not going to have time to cover all of the material in depth, but if you want, you can go back, look at the slides for a little more information. The main thing that we want to drive home here is the overall design of Expanse. We went with something that we call a scalable unit. We've got 13 of these. Each of these scalable units contains 56 compute nodes and 4 GPU nodes. Each of these scalable units is liquid cooled. Rather than air cooled. There's a couple of implications for that. For myself, I give once we're back on campus, I give a lot of tours of our data center, and it's always loud. It's always loud and hot because you have all of this air cooling, a lot of fans going. Here, it's going to be pretty quiet because it is liquid cooling. But even more importantly, this means that we're going to have a more even cooling of the hardware. Data centers tend to find that even today, that the hardware at the top of the rack tends to fail more often than hardware at the bottom. The reason is that the way most modern data centers are designed is you have cold air running under the floor. You'll have perforated tiles in front of those racks. And then fans within the compute nodes will take that cold air, pull it through the nodes and chill the CPUs, GPUs, and anything else that's generating a lot of heat. You're going to end up with temperature gradients. So those nodes at the top of the rack are going to be a little bit hotter. So sometimes you'll see that clock speeds could be ramped down a little bit. You may take a little bit of a performance hit. With liquid cooling, we're going to have much more even cooling of the hardware. And we've seen this during our reliability testing. Before we went into production, they turned the entire machine over to me for a few days, where I just ran a whole suite of applications across the entire machine. And one thing that we noted that we didn't see to the same degree with previous machines is that the runtime from node to node was incredibly consistent. And we think that is due partly to the liquid cooling. So this is just kind of a rehash of what we covered on the previous slide. Again, each of these scalable units consists of the 56 CPU nodes, the 4 GPU nodes. Also within one of these scalable units, we have what we call full fat tree connectivity. This means that you're getting the full bandwidth between any pair of nodes of the HDR InfiniBand. Across these racks, across these scalable units, you're going to take a performance hit in bandwidth. For most applications, it's not going to be that noticeable. But if you have a really bandwidth sensitive application, say you're doing spectral elements or 3D FFTs, which involve a lot of patterns of all-to-all communications of data, then you are going to see a little bit of an impact. But within a rack, you are going to have that full connectivity. I mentioned that we have connectivity to research and engineering networks. This is really important because it gives Expanse great connectivity to the outside world. Again, not going to go through all the details here, but really focus on the right-hand side of this figure. You'll see that we're connected to several 100 gigabit networks, the PRP, ESNet, Internet 2, Scenic. And we also have, it's a pretty small pipe, but a 1 gigabit connection to Amazon Web Services, which we're going to be using for the cloud bursting. Also notice that we have for what we call data mover nodes. We're going to be talking about this, I think, at the end of the day. There are efficient and inefficient ways to move data to and from Expanse. I'm going to say the worst is just to go to the login node and do secure copy. That's great if you're moving small amounts of data, but that's not how we want you to move gigabytes or terabytes of data. We have 4 special dedicated nodes that we call data movers that you're going to be using when you do the larger data transfers. Okay, getting a little bit into the AMD EPYC processor architecture. So this is the processor looks very different from what we've seen in our previous generations of Intel hardware. Normally the processor is one monolithic die, which is a great design idea, but it could be expensive. It makes it hard to scale it up. It makes it difficult to get a lot of cores onto a die. AMD took a little bit of a different approach. Here they build the processors from multiple, I guess what we call them chiplets that are connected to each other, I/O and they're connected to memory, to I/O, and to each other through AMD's Infinity Fabric. We've got a lot of bandwidth on each of these processors, 8 memory channels per socket. This is DDR4 memory at 3200 megahertz or 3200 mega transfers per second. We've got a lot of PCIe Gen 4, providing up to 128 lanes of high-speed I/O. Move on. So I mentioned this already, that the processor is made up of multiple core complex dies. So we have 2 core complexes per CCD. We have what they call the Zen 2 cores. Within each of these core complexes is going to be sharing an L3 cache. So the entire processor has 256 megabytes of L3 cache. But what's different than that we had in other processors is that this L3 cache is actually distributed. And then each core is going to have its own private 512 kilobyte L2 cache. So through the BIOS settings, the processor could be configured in different ways. Again, not going into too much detail here, but the most common configuration for HPC workloads is what they call NPS4, is where we break the operate the processor as 4 NUMA domains, non-uniform memory access domains. Again, this is something that you can't control. It's set by our operations staff, but it is going to give you the best performance for most HPC applications. The reason I even bring this up is that this has implications for how you're going to get best performance for your codes. So we need to make sure that we take our processes and our threads and we have them pinned properly to the cores so that we're not, say, engaging in a lot of unnecessary data transfer. And this is something that we're going to get into in the next couple of presentations. So moving on to compilation and other software considerations. So we've done a lot of extensive testing using 3 different sets of compilers. The AOCC, this is the AMD Optimizing Compiler Collection. These are built on the LLVM project. So if you've ever heard of Flang, the Flang and the Clang compilers, that's actually what AOCC is. The GNU compiler collection and Intel compilers. We also support multiple implementations of MPI, including MVAPICH2, OpenMPI, and Intel MPI. We'll go over this in the session on compiling your codes, but you definitely want to make sure that you specify the architecture flag when you are building your applications for Expanse. If you're using the AOCC or the GCC compilers, you want to use the -march equals ZEnver2 flag. So this is for the Zen version 2 cores. If you're using Intel or the older GCC compilers, and I think that the 10.2 is the default now, you want to use -march equals core-avx2. Really worth noting here is that you do not want to use -xhost. I had a couple of applications that I just ported over from Comet to Expanse that were using the Intel compiler. And I didn't change my makefiles or my compile lines, and I still had the -xhost in there. That doesn't appear to be recognized, and actually had some applications that ran about 5 times longer when I used -xhost. I thought it was a problem with the Intel compiler. I went back, noticed that I didn't set the -march flag, and once I did that, performance for my apps was just about the same as what I saw with AOCC. Runtime considerations. We talked about the complexity of the AMD processor. You're going to want to use binding options such as map by core, IMPI pin, or IMPI pin domain. For OpenMP, you want to use affinity options like GOMP affinity or KMP affinity. And then for hybrid codes, which we're seeing more and more of, so combination of parallelization at the process level using MPI and threads using OpenMP, you want to keep threads on the same NUMA domain as the parent MPI task. And yeah, we're going to be covering this a little bit in the next few presentations. And that's all I want to say there. Okay, so talking a little bit about benchmarking of applications on Expanse. So we benchmarked a lot of apps before we put Expanse into production. We're finding overall that things are, that the system is operating fantastically. So, here's Partialist, Gromax, NAMD, our molecular dynamics codes. Neuron is a neuroscience application. OpenFOAM for CFD, Quantum Espresso for material science. RaxML and Astral for phylogenetic tree construction, and WARF, which is a weather code. Found overall that the performance was great. On average, well, I shouldn't say average, there's actually a range of performance gains, but we find that they vary from getting the same per core performance that we had on Comet to almost 2 times faster per core compared to Comet. And again, overall throughput is expected to be easily more than 2x of Comet. We also did a lot of benchmarking of GPU applications. NAMD, Amber, and Gromax, these are MD codes. TensorFlow, PyTorch, and MXNet are deep learning framework. Beast is another phylogenetic tree construction code. And we're seeing that that when we run on Expanse is V100s compared to Comet's P100s, that we're getting a speed up of better than 1.5x. So I think even though it doesn't look like we have a lot more GPUs in the system, given that the V100s, there's going to be a lot of GPU computing power there. On the GPU nodes, just a quick glance at the architecture. All I want to point out here is if you look at the figure where we have GPU 0, 1, 2, 3 across the top, 0, 1, 2, 3 down the left, that each of these, each GPU is connected to the other GPUs through a pair of bonded NV links, which again means that if you were running multiple GPU applications where the communications between those GPUs is important, this is going to give you great performance. Software stack. So we're going to support a broad application base. So we're going to support a broad application base, just like we did on Comet. So you're going to see packages for bioinformatics, molecular dynamics, machine learning, quantum chemistry, structural mechanics, visualization. You should also mention a range of compilers, MPI libraries, math libraries. So pretty much the application stack that you see on Comet is going to be replicated on Expanse. So if you are using our software, if you're using our builds and installs, it should be a very easy transition for you. One of the details under the hood is that we're maintaining the software stack using something called Stack, and we're going to continue to have support for Singularity containers.
Hey, Bob, we're just getting up to about 9:30, so.
Okay, all right. We did start a couple minutes late, but I should finish with the next 2 minutes.
Bob, you should be okay. I mean, I have some buffer, so it should be fine.
Okay.
Okay,
So
great.
talk a little bit about the innovative features. Again, I'm going to go through these pretty quickly. We're going to be supporting cloud bursting. This is enabled through a combination of Slurm, some in-house software, and a third-party package called Terraform, which essentially gives you a standard way to define cloud resources. Again, we currently have things configured so that we can burst to AWS, but we expect that since our approach is cloud agnostic, that we're going to be able to support the other major cloud providers. But you're still going to submit your jobs directly via Slurm or as part of a composed or a composable system. So composable systems, this is I think the most novel feature of Comet. So not Comet, Expanse, still caught in 2020. Most of the nodes are going to be managed by Slurm, through traditional batch computing. But a portion of the system could be carved off into a Kubernetes cluster. This is going to allow you to put together what we call composable systems, where you bring in both resources from Expanse and external resources into a single system. We feel that this is going to be really valuable for workflows that need to access things like edge computing, FPGAs, unique resources that are not part of Expanse. And we actually have funding through the advanced user support to support the development of composable systems. I'll just go through this very quickly. We are fully integrated as an Exceed level 1 resource. We're going to have about 6 months of overlap between Comet and Expanse operations. We do have a new program, HPC at MSI, targeted at the minority serving institutions, where they can get access to relatively small amounts of time through a director's discretionary award. And the expectation is that they would then graduate to writing proposals to Exceed. Again, we have advanced support available from our staff for cloud integration and composable systems. And we're going to be working with Exceed to develop review criteria for these innovative elements. You're going to go pretty quickly here. Allocations, not going to go into too much detail. I think I've said it a few times already. If you're already familiar with the allocations process for Comet, it's going to be pretty much the same for Expanse. Startup and educational requests are going to be reviewed continuously, larger research awards 4 times per year. Just point out that there are 3 resources related to Expanse. So Expanse is what we call the CPU component of the machine. Expanse GPU is a separately allocated resource. And then we also have storage allocations, SDSC, Expanse, project storage. To just show where you go to submit jobs, you go to the Xseed portal, submit review request. This will take you to XRAS, and it's going to be the same interface that you've seen before. Again, you'll see 3 resources: Expanse, Expanse GPU, and Expanse project storage. So with that, I'm going to wrap up. Expanse, again, provides a substantial increase in performance and throughput relative to Comet. It's really an evolution of the Comet design with the additions of some innovative features like the cloud integration and composable systems. We're also going to be having support for high throughput and distributed computing through the Open Science Grid. Talked about the hardware already, the AMD processors, the NVIDIA GPUs, fast interconnect, and then finally follow all things Expanse at the following URL. And that is it. I'm happy to take any questions.
Yeah, Bob, there is a question on the chat if you can take a quick look.
Okay, well, no. Can you point it out for me? I'm looking through and I see 23 messages that
Yes,
came.
that's right. You've got so the very most recent one was I was told to request a transition allocation to Expanse. This person has some Comet time, but they won't be able to use. And is there a specific allocation process for that, or do they have to do a full allocation request?
Oh, a transition.
So I think
Transfer.
Bob, yeah, I replied to
Transfer
the
request.
Okay, good.
So you can
Okay,
do a
good. Yep,
small
see.
transfer, basically. Pascal, it's at the same place. But instead of doing a new allocation, if you click on your existing allocation, there are action buttons. And one of the actions is a transfer, and you can just do it's like a regular transfer you used to do on other machines, basically. So you can just request a transfer from Comet to Expanse, and you probably don't need a lot to get going. So just do enough so that you can test things out. And eventually we will end up transferring remaining time to Expanse anyway. So.
Okay, great. Thanks, Mahidar, for covering that. Do we have any other questions? If not, I will stop sharing and we'll see if Mahidar can get us back on schedule.
Thanks, Bob. Yeah, I think it should be okay. Let me see if I can get my slides shared. So does everyone see my slides?
We see presenter view, Mahidar.
Yeah, we're seeing the presenter interface.
Oh, okay. I'm just going to swap display. Okay. Is that better?
Yes.
Okay, great. Let me just pull this stuff off here. Okay. So yeah, today I'm just going to talk about running jobs in Expanse and point out some of the differences that you see between Expanse and Comet. So if you're used to Comet, what kind of changes you can expect. Oops. Okay. So the outline is basically, I'll do a quick system overview. I mean, we just saw the talk from Bob, so this is more for completeness. So I'm just going to whip through the 2 slides just in case someone comes back to this individual talk, they can look at that. And then look at the Slurm scheduler details, specifically the partition information. And then we can go through some examples of different kinds of jobs that we will look at. So like MPI, OpenMP, hybrid jobs, GPU jobs. And I have some specific examples for file systems, specifically the local scratch usage, and then we can conclude on that. So let's start by looking at the system. We already did this, so I'm just going to quickly go through that. Basically, as Bob said, everything is in scalable compute units, and we have 28 standard compute nodes and 52 GPU nodes. So what we're going to look at is we can look at how to use these resources. So let me go there. And the SSCU, which is the scalable compute unit, is basically designed so that most of your long tail kind of jobs fit in one rack, less than one rack. So our limit on the job size on the compute nodes is 4,096 cores, and that fits easily within a rack, basically. And each rack has 56 compute nodes and 4 GPU nodes. And I think that might be enough for that. So in terms of how do you access Expanse, logging in, the CPU and GPU resources are allocated separately. But the login nodes are the same. So if you want to log into Expanse, you can use the hostname login.expanse.sdsc.edu. That this round robins between the two login nodes that we have. And one thing to keep in mind is the login nodes are the AMD Rome-based nodes, and the GPU nodes are different from that. So, so when you're compiling, you need to compile on the GPU nodes. But other than that, just log into the nodes as you would on Comet. And users can log in directly using SSH. And you can use any SSH client. If you're on a Windows machine, you can use PuTTY, for example, or some people use WinSCP. Any SSH client would work. When you log in from the Exceed single sign-on host, you can GSI SSH. Actually, now you don't need the full thing. You can do GSI SSH Expanse. And there's also access via the Expanse user portal. Subha will talk about that later. So one thing you could do is you can use SSH keys. We are set up to authenticate with your Exceed portal account if there's a mapping, but you can also add SSH keys. And our preference is if you add an SSH key, make sure you have a strong, is to use SSH keys and also make sure you have a strong passphrase on the private key on your local machine, and don't copy this private key around. Keep that only on your machine, and use SSH agents or keychains to avoid repeatedly typing your private key password on your own machine. And the host that, one thing we do have is we have a limit on the number of SSH connections that come in on the login node. So if you do more than 10 times per minute, I think you might get blocked for a short period of time. If you're a gateway and you need an option to work around this, please let us know, and I can give you some. We can give you some workaround for that. In terms of the other option is we do have two-factor authentication with Google Authenticator as an option. So if you are concerned about having two-factor, and you can set that up, and we have the example set up on the Expanse website. One other thing I want to say is you should look at Scott's webinar on security, and there's a link there with the recording. So now you logged in and you're on a login node, and we want to make sure you know what appropriate use of login nodes is. Basically, they're meant for simple file editing, simple data management, and tasks that use minimal compute resources. So you can do a compile if it's lightweight and doesn't use a lot of cores. You should be able to do like compiles like that. You can do simple things like move SCPs or moving things. I mean, cloning Git repos, those sort of things are okay. But please make sure you're not running some computationally demanding job on the login node. It's not meant for that. They have 128 cores, but we do have hundreds of users logged in, so we don't want people running jobs on the login node. And same goes for compilation. And the reason I put that in there is that there are some frameworks where you might end up, like, for example, if you're doing a spec-based build, it might look at the 128 cores and try to use all of them. So you want to either limit that specifically or use a compute node if you really want to scale up with the compile task. So just to summarize, basically, don't run anything computationally intensive. Don't run any intensive workflow management tool there. You can always run the workflow management tool externally and use SSH to submit jobs on the node. So that is okay. And then if you're doing any heavy data transfers, don't do that from the login nodes. We have dedicated data transfer nodes for the large number of transfers. You can use Globus for large transfers, or you can, we have an OSS-DM-interactive node that will be available for interactive use. Either way, don't run huge data transfers on the login node. One other thing, don't run any service that is making, like your files or some other thing accessible to the internet on the login node. So I think, and then same thing goes for Jupyter Notebooks. We have a whole setup for running Jupyter Notebooks, and we can point you to information on that if you want to run Jupyter Notebooks, but please don't run them on the login node. They take up resources and also open you up to security issues if you just run it directly on the login node. For GPU codes, if you're compiling things, as I mentioned, you should request interactive sessions on batch nodes. We have a GPU debug partition that I'll talk about, or regular GPU partitions, so that you're getting the right CPU that you compile with, because the GPU nodes have Intel Cascade Lake processors, so you don't want to be running AMD compiled code there. So you should compile on a GPU node for that reason. And also some of the GPU packages are available only on the GPU node, so that's another reason we should use the GPU node. So that was a quick overview on the system itself and how you log in and everything. Now we run Expanse uses the Slurm scheduler, which stands for Simple Linux Utility for Resource Management. And so if you're running on Comet, you're used to Slurm. We just have a newer version on Expanse. So there are some differences in the way you run, but overall, you should be pretty familiar with Slurm if you've been running on Comet, and not much will change in that sense. So if you're submitting job, you can use sbatch commands. If you're checking job status, you can use the sq command. And I have gone through some of the scenarios, basically checking job status and how you can cancel a job. One other difference I want to point out, on Comet, we had PBS compatibility wrappers installed. We do not have those installed on Expanse. So don't try to use qstat and some of the commands that came over from the PBS side. They're not going to work. So basically get familiar with the Slurm equivalents of them if you've been using them on Comet. In terms of the setup, Expanse has both node exclusive and shared partitions, just like Comet. So if you're familiar from Comet, we have the compute partition, which is for the CPU nodes. It's exclusive access. And I have this in red because we've already seen some people do this and run out of time. So please be careful that this is now 128 cores. So if you do not need all 128 cores or you do not need all the memory on a node, please don't use the compute partition because you're going to run out of time real quick if you burn 128 SUs per hour. If you need 128 cores and your code scales, of course you can use it. And or if you have multiple nodes, multi-node jobs, of course you can use it. But just be careful about what you're running on these exclusive nodes. Shared nodes have basically shared access, so you can run with anything less than 128 cores, you can run there. And similarly on the GPU node, you have GPU partition and the GPU shared partition. Again, GPU is exclusive access and GPU shared is shared access. So you can ask for one GPU, for example, in the GPU shared queue. And this is, again, very similar to what was there on Comet. We have a large shared partition, which is for large memory nodes, and then a debug partition for short tests, so less than 30 minutes. This is, again, similar to Comet. What we have new on Expanse is a GPU debug, which is for short tests and compilation kind of tasks. So you can quickly get through the queue and try out your compiles. We also have a preamp partition. This is where it's a discounted job partition, but the jobs can be preempted by jobs in other partitions. So we have an overlapped partition setup. So if you're running in preempt and the machine's full and there is a job that comes along in compute that asks for resources, your preempt job will be stopped. But if your code is easily checkpointable and restartable, this is an excellent way to save some SUs. So we also have a GPU preempt in the same vein. So that's the summary of the Expanse partitions. Basically, compute, all of them have a 48-hour limit. The preempt ones have 7-day limits. But remember, on the preempt, we have no refunds. So you really need to be sure that your code can restart if you're using that. So in terms of the limits, we have a maximum of 32 nodes on the compute node as the job size limit, which is basically 4096 cores. On the shared, you can only have single node jobs. And then on GPU, max nodes is 4. That might sound low, but we have only 52 nodes, so we have to be cognizant of sharing the GPU resources with all the users. And these nodes are really busy, so the lower limits will kind of help us get enough throughput for everybody. On the large shared node, the limit is 1 node. And also, there is a minimum memory requirement of 256 gigs. So in terms of the scheduler, what are the required parameters and what is different from Comet? So you need to specify the partition. So that's the -- partition option. On Comet, it would default to compute, but here you please make sure you specify it. And then the number of nodes, number of tasks per node need to be specified, and the wall clock. Now, one of the changes are in red, basically the account. Unlike Comet, we do not pick a default. So you need to explicitly pick an account. And there is a utility called Expanse-client if you want to find information about your own accounts. And then in the GPU partitions, you need to specify the -- GPU. One node, the -- mem per CPU and mem per GPU are not required. However, you should get in the habit of explicitly requesting this. Because the default on Expanse is 1 GB per core. And we've done this so that we can have some flexibility with memory on the shared partition nodes, so that, if there's a user with a lower memory requirement and a user with a larger memory requirement, we could fit more in a given node by doing this. Instead of by default assigning 2 GB per core, then if a user doesn't need it, that memory gets wasted. So we're trying to fit more in basically on these big nodes. So, but what I want to stress is that that's the default everywhere across the whole system. So even in the compute and GPU partitions, you should explicitly request the memory you need. So if you need 240 gigs, do a -- mem equals 240 gigs. All right, so that is the overview of the partitions. So how do you actually run? So interactive jobs, this should look familiar to anyone using Comet, except for the different more partitions that are available, but you can essentially do the same thing you did on Comet for getting an interactive session using the srun command. So like I have an example here for one regular compute node, 128 cores in the debug partition for 30 minutes. So you just do -- partition equals debug, nodes equals 1 and task per node equals 128. And notice I'm putting -- mem equals 248 gigs. And 248 is the largest amount you can ask for on the compute nodes. And I have the -a XYZ123 there. That's basically the account. You need to specify it, unlike Comet, which would pick up the default. Here you have to specify it. Similar thing on the GPU nodes. There's the -- partition equals GPU shared and so on. One thing I should say is that on Comet, we were using gress for the GPU request. Here, we are doing -- GPU equals 1. So you need to specify the number of GPUs there. So I think someone caught the difference between the partition limits. I think we did increase it to 30 minutes. I will double check that. So the next thing is an example batch script. So if you've been running on Comet, it should look very familiar to you. So we have basically partition equals compute, nodes equals 2, and so on. And see, out here, I've actually used a mem per CPU equals 1800. But that's, you could either do mem per CPU or you can do -- mem, and then the account needs to be specified, as I said. And after that, it's very similar to what you did on Comet. You set up your environment. So I'm setting up the modules, and Marty is going to talk a lot more about the modules, so I'm not going to go into it here. But one thing to remember is that there is a module for Slurm. So if you're purging, remember to load the module for Slurm, because that's needed for all the Slurm pieces. So, and then you do, so srun -- MPI equals PMI2, that's fine. And then N 256. And I have a CPU bind option here. But you can use other mechanisms to launch MPI. For example, you could do an MPI run with flags. And I think I have some examples with a mixed. Oh, so I see a question about what module purge does. Module purge just cleans out everything. And one thing I should say, and maybe I'm stealing from Marty's talk a little bit, but don't put any module loads in your Bashrc, but set up everything in your batch script. And by purging, we are essentially cleaning everything that's loaded and then starting afresh, and then you load exactly what you want for this particular job. So you have to get into the habit of doing this because the software stack for the GPU nodes is completely different from the software stack for the CPU nodes. So you kind of need to make sure you're getting in the habit of doing this instead of trying to put this in your bash RC or some other place, because that's going to cause issues because the stack's different. For an OpenMP job, one thing here, I think the Slurm on Expanse might be much stricter in terms of how it gives you the cores. So you shouldn't do nodes equals 1 and then task per node equals 16 and run a OpenMP job. Actually, OpenMP might be okay, but if you have a mixed job, you're going to get in trouble because it's going to bind the job to the first core. So if you want 16 threads, you can basically do n task per node equals 1 and CPUs per task equals 16. That way, the scheduler knows each of your tasks is going to spawn 16 threads. I see a question about srun being equivalent to MPI run. Yeah, I mean, srun can do other things, but yeah, MPI is one of the options there. Yeah. Yeah, you can ignore the -n if you use some other options. That's fine. And so that's basically the OpenMP job. Now, for hybrid MPI OpenMP jobs, one thing I wanted to go back to is basically recall the setup on the machine. It's of the processor. Basically, it's partitioned. It's got 8 CCDs, and then each CCD has 8 cores. So the way the partitioning happens is on the node, we have 4 NUMA domains. Each logical quadrant in this picture is a NUMA domain. So if you look at the rightmost picture, basically you see the L3 cache being shared across all the 8 cores, but then the L2 cache is basically the L2 cache is shared among 4 cores actually, and so your memory is kind of so there are options to set this up, but the way we've set it up is an NPS4 configuration. So you end up with memory interleaved across 2 memory channels for each of these quadrants, and then each of the quadrants has basically 16 cores. So when you're running, you have to keep this in mind. So you can either go when you're running hybrid jobs, you're either trying to match to the L3 cache so that the 4 cores that you're, 4 threads that you have share the same L3 cache, or you try to basically make sure that you're at least on the same NUMA domain. So you don't want to be going across NUMA domains if possible with your hybrid jobs, with the threads. So you have to keep that in mind. There are pinning options both with the MPI run and also with like for Intel MPI, for example, there's an MPI pin domain option. If you go look at the OpenMPI related MPI run, there is a map by L3 cache option. So in this example, for example, what I'm doing is 2 nodes, 32 tasks per node, and then 4 CPUs per task. So what I'm expecting this code to do is have 4 OpenMP threads. And what I'm saying is map those threads so that they're bound to the same L3 cache. So that's what this is doing. This becomes important for some codes in terms of performance, and it will be very code specific, so you'll have to test and see if it helps you or not. For example, WRF is one case where it might help to make this kind of binding. So that was on the CPU nodes. Looking at the batch script for a GPU node, again, if you've been running on Comet, you've probably seen this sort of script many times. You basically have the partition GPU shared. Here I've just asked for one task. You can ask for up to, I mean, you can ask for more tasks, but basically, if you're running a primarily GPU thing and say you only need one task, this is fine to do. I haven't requested memory here, so I'm going to end up with 1 GB, but the GPU nodes have a lot of memory. They have 384 gigs of memory, so you could go up to 90 gigs on one if associated with one GPU job, for example. You can even go more than that if you require it, but so you basically have options there, but the thing I want to point out is the dash dash GPUs equals 1. So if you recall your Comet script, it's going to say dash dash gress equals GPU colon P100 colon 1 or 4 or whatever, right? So in this case, that goes away, and then you have a dash dash GPUs equals 1. Other than that, everything looks the same. And similarly, for a multi-node job, you do nodes equals 4, and I'm saying, okay, I need one task for each GPU, so I'm saying and task per node equals 4, and let's say that that task is spreading, spawning 10 threads, so you do CPUs per task equals 10. And here I'm asking for the whole memory, 370 gigs. But one thing to keep in mind is that the GPUs now says 16, so this is very different from Comet, because on Comet, you had to match the number of GPUs on the node, and then it would get multiplied. But here you're doing GPUs equals 16, which is the total number of GPUs you need. So, so I see a question that says the code document for a research allocation on Expanse will be much more complicated. Not necessarily. If you're sticking to one type of, like say you're just doing CPU computations, then it's just very similar, right? You just have to redo your scaling study on Expanse, but with the AMD CPUs. I mean, it's more, I think the binding aspect and all these things don't need to really go in the code document. Yeah, it's more for you to get the best performance out of it. So yeah, maybe testing will take a little longer because you might have to figure out what the best approach to running is. Is it hybrid? Is it like a pure MPI job? Is there some parameter that you need to set? But all that doesn't really go in the code document. In the code document, you can talk about the scaling results that you're getting and the performance you're getting. So the last piece I want to talk about is the file systems. So the home file system. So after logging in, you basically land in your home directory, and it's referenced by the environment variable $home. And the home directory is limited in space. You have 100 GB of quota, and really should be used only for source code binaries, maybe small input files. And for some kinds of codes, if you're not doing intensive I/O, it might be okay to run from there, but you have to be careful about it. Just make sure your I/O load is not a lot, very intensive. So don't run anything that does intensive I/O. For example, if you have a code that writes out a file from every core, and you're running with the, say 512 cores, don't write that to the home file system. You're going to cause a lot of I/O issues. So for such kind of things, you should use Lustre, or you can use the local scratch, and I'll talk about the local scratch a little bit later. So the parallel file system is basically a Lustre-based file system. It's 12 petabytes. It's a single file system. That's one thing to remember. There are 2 locations which have different policies, but the actual underlying file system is a single file system. It's 12 petabytes and 140 gigabytes per second. So there are 2 locations on Expanse, very similar to what you used to have on Comet, except on Comet there were 2 different file systems. On Expanse, it's the same file system but with different policies. So there's a Luster Scratch location, which is /expanse /luster scratch and then $user. And this is purged for files older than 90 days based on create date. So truly this is meant for Scratch. So, and I know on Comet we've been kind of asking users to clean up and do the managing of the data that way. But on Expanse, it's going to be very different. We are going to do this purge, automated purge. So please be careful about what you leave in there. Don't put anything that you need long-term in the Scratch location. And the projects location is more the allocated storage. So when you get an Expanse project storage allocation, this is where you would put it in. And this won't be purged during your active allocation period. And we will give you, I think, 3 months after an allocation ends to get your data off. But so if you expect, like, say, you need a terabyte of data that needs to be there for, like, say it's a kind of some kind of reference data set that needs to be available for all your jobs. And you need to put that in this kind of location so that you're not having that purged on the Scratch side. And so if you anticipate needing, like, say, 10 terabytes that needs to be available throughout your allocation period, just please make sure that you request that on the allocation request. We also limit the number of files that can be stored in this file system to 2 million files per user. Again, this is because the file system is primarily good at like large block I/O. So we don't want millions of small files on the file system. It slows down the metadata servers and it slows down the response on the file system when you do file management with directories with thousands of direct files and so on. We do have a little bit better setup on Luster with the hardware. We have 4 metadata servers versus the 2 we had on Comet. And on the metadata servers, we have NVMe. So with a progressive layout so that you can get a little, not little, actually quite a bit faster IOPS performance. That said, if your workflow needs a lot of small I/O, you should try to use the local NVMe Scratch, which brings me to the next slide, which is basically all Expanse nodes have NVMe-based local Scratch storage, and the disk sizes kind of vary depending on the nodes. The regular compute nodes have 1 terabyte, about 900 gigabytes usable. Large memory nodes have about 2.9 terabytes usable. And then the GPU nodes have about 1.4 terabytes usable. This is excellent for like IOPS intensive workloads. Also, like if you have like your codes create Scratch files, small and large is fine, anything is fine. But if they're generated on a per task basis, this is a nice way to put it in. So I see a question that says, will Luster on Comet be mounted also on Expanse for? No, so they're mounted on the Globus backend servers. So if you're doing a Globus-based transfer, both of the file systems are mounted there, both the Comet and Expanse. So whether you use the exceed pound Expanse or XP pound Comet endpoints, you should see both the sets of file systems there. So going back to the local Scratch, basically this local Scratch can be accessed only during a job execution, and it's /scratch $user job underscore slurm underscore job ID. Again, this is slightly different from Comet. We didn't have the job prefix in Comet, so if you're copying over scripts from Comet, just make sure to change the location. It's a little bit different. The location is basically purged at the end of a job. So any important data must be copied out. Just as an example, so if you're trying, say like Gaussian is a good example. It creates a lot of scratch files, and there is actually a variable that it checks for scratch location, Gauss underscores scrdir. So pretty simple to use the local scratch. Just change the location to point to the job specific local scratch. Um, and a lot of codes will just go out of the temp dir directory. So you can set the temp dir variable, and that should be sufficient for a lot of codes. Now, in some cases, that might not be easy to use. Like it's not like, you just set a temp location and it works. You may have to copy things over and so on. And that's fine too. I mean, and this is an example that shows how you would do it. So like one thing to remember is any commands you run in the Slurm script without an MPI wrapper or an srun wrapper will run only on the particular node. So the primary node. So if you're say on a multi-node job and you want to copy the local scratch on each, you need to either use srun or MPI run to kind of do that across all the nodes. But anyway, you can copy the binary to the SSD. So I see a question about the space limit on the Lustre Scratch. We do have a limit of 10 terabytes, but we can raise that if you end up requiring it. But yeah, it is regularly purged, so we could go up a little higher than we would on Comet. So in terms of the local scratch usage, so you could copy things into the local scratch in your script, change to that location, run your job. Maybe you get some output there, you can copy it back. One thing I should note is you need to make sure that either this command that you're running finishes in the in enough time so that the copy back can happen. Like say this is a 30-minute job and this MPI run takes 40 minutes, then you will never get to this copy back, and then everything that's sitting in the local scratch will get deleted. So if you say you're running something that you run to the end of the clock and then restart, and your restart files are in the local scratch, what you could do is add a timeout command right ahead of this MPI run. So you could say timeout 28 minutes and basically, and then the MPI run. So what would happen then is that the task would get killed at 28 minutes, and then you would get to this copy command at the end that will copy out things. So you have to remember this is a bash script that's running, and if it doesn't get to this line, then the copy back won't happen. And once the job's finished, the data is gone from local scratch. So it's quite important to make sure you copy it out before the job finishes. So to summarize, basically we use Slurm for scheduling jobs. Everything should be run through the scheduler. Don't run on the login nodes. We have both node exclusive and shared partitions, just like on Comet. Unlike Comet, you have to specify the account information specifically. There are several file system options, just like Comet. You have Lustre and you have NVMe-based local scratch, which is a lot faster than the SSD on the Comets, by the way. So you should look at that if you're running. There are a lot of example scripts that we are putting in CM shared examples SDSC for like common applications. You'll see one for Amber, for QE, NAMD, and so on there. And we'll keep adding to that. And if we see some things that are missing, let us know with our ticket, and we can try to add examples. And basically, we've been in production since December, and we keep updating our website. So please follow along at expanse.sdsc.edu. One thing I should note is that since this is a new processor and a new kind of architecture of the processor, there's going to be optimizations ongoing. We regularly work with AMD in a user forum, and we've always given feedback like for development of packages and so on. and AMD's been providing optimized versions of SPAC versions of the packages. So time to time, you might see us put in more optimized versions of something that's already there, and we will update when that happens. And so I think at that I'm done. I'll take a quick look at the questions to see what I may have missed. I think there was a question of the Stripe file system on Expanse. Yeah, that might be beyond. I can say that it's looks very similar striping wise. It looks, I mean, it's a Lustre file system, so you can use the same kind of striping commands. The one difference is your metadata is actually striped across 4 servers, so you might see a little faster performance as a result. And that's not something you change, but you'll see that. The scratch limit we talked about. Let's see.
There was a question about purge policy. Did we cover that?
Oh, what was that about?
Purge policies on the file systems.
Oh, did I not?
I don't know if you talked about it.
I say
Okay.
I'll go over it again in the later session.
Oh, okay. Yeah. Basically, it's 90 days from using create time. So no touching of files, please. It's not going to help, basically. And so it's 90 days from create time, only in the Expanse Lustre scratch locations. And yeah, we haven't done the first one yet, but we will warn before we do the first one. But please do remember that this is different from a Comet, and it's going to happen, and you should plan on not leaving anything important in the scratch location.
Hey, Mahi, I'm going to step in. We're 4 minutes into our 10:15
okay.
break. That's okay. So let's return back about 10:29.
Yeah, I can reply to
Roughly
the
about
last
10
question
minutes.
on the email.
Yeah,
Yeah.
Yeah, we have a Q&A session at the end of the day too, but
Oh, yeah, that's right.
let's all return back in about 10 minutes
Sounds good.
and
Thanks.
get started with Marty.
Just get set up here. Okay. Can you see the slides, Jeff? Is everything look good? Okay, great. Yeah, thanks everybody for attending the Comet to Expanse transition tutorial today. So my talk, it's a little different, probably maybe from what the blurb was in the description of the tutorial, but I think it's a useful topic to. I mean, it's related to what we're discussing with the module environments and how to access software on the system. But I get, only a few occasions a year to sort of talk to users and this many users directly about some of the things that sort of, we see common issues that people have when using Comet or Expanse and other Exceed systems. And the common thread that, using the software module environment and, just getting your work done on the systems really comes down to understanding how to manage your what I'm calling your HPC software environment. And we spend a lot of time in our group, in the HPC user services group, building and installing software for you to use. And that's what this module environment is used to help you access that software. But there's plenty of other software that users, want to run on our systems that we don't build and maintain for you. But, there's other things like Anaconda, or if you're a Python user, there's the pip installer, or if you're an R person, right? There's a built-in installation method for managing the software packages that you need. And so what I wanted to do in this talk is sort of expand beyond just, the module environment that we have, and I'll cover that and some of the differences that you'll see from Comet to Expanse. But I also just wanted to establish sort of a baseline set of definitions and ideas in your head that might teach you a little bit about how to think about managing the software that you use in a reproducible way on HPC systems in general. And yeah, so that's kind of my goal for today. And that's kind of, if I go to the first slide, why is it not advancing? Oh, Jeff already covered the exceed code of conduct. And this is kind of the second iteration I've tried to sort of make of this presentation. So it's kind of a new topic that for me, teaching wise. And so I haven't sort of sorted out all of the threads and connected them together that I want to, but this is kind of the second version of sort of trying to pull those things together for you. And when it comes down to also the topic for this talk was supposed to be some sort of code compilation and optimization stuff. And I'm not going to touch too much on this. You can kind of consider getting your software environment right as the 0th order thing you need to do to have your software run optimally on the systems. If you can't manage your software environment in sort of a consistent way, you're going to probably run into bad performance issues anyway if you're not using it appropriately. So that's why I'm sort of more focused on the environment here. And these are the questions that hopefully you'll have, some better idea of if you don't understand some of the topics that I talk about today, like what these questions mean and why they're important for working on our systems. Let me just get my clock here so I can see the time. So we have about an hour to go through this, and I'll go through some of the slides to sort of motivate answering these questions, and then I'll do sort of a live demo, walk you through kind of what the software environment on Expanse looks like, and talk about some of the things that the concepts here in the slides and how they relate to what you're going to see on the system and how how to make use of it. But if you are really interested in, sort of code compilation optimization, I would definitely recommend you look at our upcoming events on the education training session. There's Bob is giving a talk in, I think, 2 weeks on sort of profiling your code on Expanse using AMD's UProf tool. And it's kind of their sort of code optimization for their architecture, profiling tools that you can learn a little bit more about if you're really interested in that kind of stuff. And also in April, we're doing a special AMD specific training to get more into how to use the EPYC architecture, the issues you'll see compiling code with the AOCC compilers and their specialized math libraries, if you're not familiar with them. We're getting familiar with them ourselves, and so we'll be, going through that kind of stuff in detail in about, in 2 months from now. But for today's talk, this is kind of what brought us all together, probably the conversation at some point, where you had to run someone else's code on an HPC system, and eventually maybe you got good at it and you're pretty expert here. Maybe you're just getting started, but at some point you had to run someone's code or your code that you developed on an HPC system to get your science done, right? And when you're starting out, it can get kind of confusing, right? Maybe this is what you feel like sometimes when you're trying to install your software packages on a new HPC system like Expanse, right? Things are different from system to system. If you've worked with enough different HPC systems, you've definitely come to the conclusion that they're all quite unique sometimes, and you have to really get into the nuances and maintaining what your software environment looks like on the different systems is unique to each in some sense, right? Because there's different software on different systems, and it can become kind of an issue. And like that cartoon, it's funny if you're a Python person, it probably makes sense to you. But I kind of tested myself when I was developing these slides the last day or so, and how many different versions of Python can I fit on the systems that I use day to day, right? I have working on a Mac right now. I have one version of Python there on my local machine. I log into Expanse. There's another version of Python when you log into Expanse. There's also another version of Python in an Anaconda module on Expanse. And the same thing is true on, on Comet. There's different versions of Python. One of the most common questions we get is, where's Python 3 on Comet? It's in the Python 2 module 2. So, that's one thing that'll be different. It'll be much more clear where your Python is, hopefully on Expanse eventually. But, these are like the common environments that I work in every day, and trying to keep track of what software you're using is important for scientific reproducibility, right? If we're here doing science and engineering, you want to make sure you can run your code in a reproducible way, and know how to deploy your software on different systems, regardless of what these different software environments might be. And so there's a lot of complexity that can get into this, but you should embrace trying to get comfortable. It's like you have to sort of understand what software is around you on these different systems and how to utilize it correctly. And so just the general definition, I would say, of a software environment is really the ecosystem of software packages and libraries that you depend on to run your applications, right? And there's different layers of the software, what's in your software environment. It affects how your code runs and your day-to-day work, right? There's software packages and libraries that you use from the operating system every day. There's, if you're developing software and compiling your own software, there's development tools like compilers, build systems. And then there's for every HPC system, there's, unique application and hardware specific software libraries, right? So one of the things that we do in our group, the HPC User Services Group, is maintain a lot of, completely built applications that are compiled and built for you, that are optimized on our hardware, right? These are usually common applications that many users use and aren't familiar necessarily with, aren't the type of users that necessarily are familiar with compiling their own software, but we provide that for you, right? And as I mentioned, software environments are really kind of unique to each system, but you can modify them to support the applications that you want to run, deploy and run for your work, right? And so that's the this nebulous term of software environment kind of gets tossed around a lot, but it's really just this ecosystem of software packages that you rely on for your application, right? And each environment that you create, right, can be different for different applications, right? And this is, in a practical sense, what is your software environment? It's, what I would say is you want to think about it anytime you open up your terminal and log into Expanse, and in that window, right, that is an individual software environment, right, that you can now manipulate and change to run your code on Expanse, right? And if you're not familiar sort of with Linux environments, if you're coming from a Windows system or you're just new in general to running on HPC systems, right, all the systems really run on a Linux based operating system. And when you open a terminal and log in, what you're running is called a shell program, right? This is your user interface for Linux and other Unix-like operating systems. Like if you're on a Mac, you've probably used the terminal application to, interact on the command line with the software on your local system. If you're a Mac user, you probably use like Homebrew maybe to install packages on your own system and modify your software, your local software environment on your laptop with say Homebrew, right? But the shell program is really the program that's you're using to interact with your operating system and the software environment that's available on any given system, right? It's your sort of fundamental user interface, and that's what you're using every time you log into Expanse. You're running a shell program, right, in that terminal. And there's different types of shell programs. The one that's the default on Expanse and Comet is the Bash shell. It's probably the most common. I think it's probably the default on most Linux distributions as far as I'm aware. But people get used to different shell environments, and we do have different ones available on Expanse and Comet. The one thing is that this has to be changed kind of at the back end level, and we have to sort of modify some configurations for your user account. So if you do want a different shell at some point in the future, you just have to send us a request through the Exceed ticketing system, right? And so, but every shell has, a set of common things that it sort of has and does, right? And one of these things is shell built-ins. You're all probably very familiar with them. It's, things like the cd command, the make directory, the mkdir command, like make directories. These are just built-in functions that, are sort of self-contained little programs that run inside the shell. They're not external to the shell program itself. It's the functionality that provides your access to interacting with the system that you're on, right? So if you want to move to a different directory in a different part of the file system on Expanse, the cd command, or if you need help to look at the manuals, that's also a built-in kind of command, right? So there's built-in commands. There's if each shell you should really think about, is its own running instance of a shell program is really like what we would call like a shell session, right? So here I'm running two different terminal windows, with one open with Expanse on the left and another one logged into Expanse on the right. And these are both different instances of a running shell on Expanse, right? And so depending on which terminal I'm in and which commands I issue, I can change my software environment within those individual shells, right? So they're individually modifiable, these sessions, right? And that will affect the software environment that you have depending on the commands that you issue there, right? So Mahi mentioned briefly, the use of if you're familiar with the Bashrc, which I won't really talk about in this talk today, but the Bashrc file. This allows you to sort of set some defaults for each individual default, run some default commands to configure your shell when it starts up each time you open one of these new windows and, start a new shell session essentially, right? And, that's not a good practice because in many cases, you want to have different defaults for different reasons. And the Bashrc file, while it's useful if you really do only want a single type of software environment all the time, anytime you want to change that default environment, you have to go back and edit your Bashrc. And the problem that users run into is that they forget which commands go with which environment that they wanted. And so we always recommend, you want really just a default shell session and modify your software environment from there, or in, say, your batch job script, and you're going to have a much less, less headaches over time, essentially, managing your software environment and getting your work done, right? So also, shells, in addition to the built-in commands, you have variables you can define, right? Just like it's kind of like a mini, every shell sort of has its own scripting language that you can use to manipulate the environment and work with the system that you're on. And so variables are obviously something you need for programming. And the important thing is when we talk about software environments, every shell has a set of environment variables. And so these are more special shell variables that affect how the software you use within a given shell session runs, right? And so the most important environment variables for managing the type of software that's deployed in your environment, that the software you have access to and are interacting with in a given shell session are, the first one is the path environment variable. This essentially sets a path of directories to search for executable programs, right? So if you want to run, program X and it lives over here in your home directory, what you want to do instead of what you might want to do, instead of typing out the complete absolute path to that executable every time you run, you just put the directory of where that executable lives in your path variable, and you can just, type program X, and the shell will find that binary that you've put in the path when you type it in as sort of a command on the command line, right? So this path variable really is, it defines your software, where your shell is going to look for software that's available to use, right? And so modifying this path and putting different directories in it establishes different places that the shell is going to look for your software you have access to, right? Similarly, there's this LD library path environment variable. And essentially, this is like the path variable, but for libraries that you're linking any software against, right? So when you compile software that uses, source code from multiple sources, and there's different dependencies, right? There's a set of libraries that you might use for a given package, and you might link against those in a dynamic shared library approach. And so this is where, just like path searches for executable binaries, the library path determines where your shell is going to look for compiled, shared libraries when you're running your program, right? Because it has to link back to where those libraries are on the system. All right. Now, the nice thing is if you're just using the software that we provide for you, you don't really have to do anything with the path and LD library path environment variables, right? If you've been running on Comet for years and you just use a standard package like Gromax, right? And you've always just said module load Gromax, and used the Gromax software from there, and that's all you've ever done, you probably didn't really think about, paths, your path and library path. But what's happening under the hood is, when you use the module environment, this is what helps. This is I think I should just go to the next slide. This is environment modules. These things we're talking about are a set of tools that allow users to easily manage the changing of their shell environments, essentially, right? In particular, for controlling access to different pieces of software on HPC systems, right? It's modifying the path and LD library path for you, right? So for all the software that we're installing for you on our systems, right, you'll find you don't have to manually set your path and LD library path explicitly, right? It's being done for you through the module environment, right? It's controlling where your shell is going to look for a given set of software and the different libraries you might need for that software that we've provided for you, right? So environment modules is one implementation of this sort of environment module concept that allows sort of an easier way for users to change their shell in their software environment. And these are the commands that you're used to probably using the module environment. Module lists provides kind of a list of all the packages that are in the module environment, all the software that's available there. Module avail, for specific packages, kind of a way to search for if a certain package with a given name is available. The question came up earlier, what was module purge? It's basically to clear your module environment, basically take out all of the changes to your path and LD library path and other variables that the module environment is changing. Module purge just says, get rid of it. I want to start over. I want a clean software environment, basically. I want the default, right? And then how you change your software environment using environment modules is with the module load and if you want to use unload command. I usually just purge everything and start from scratch. So module load is the command you issue to load a given piece of software that's available on the system that we've provided for you, right? Module show gives you information about a given package, and then a new command that's different on Expanse than on Comet is module spider. This is a new command that you'll want to get familiar with. This is a new way to search for a given software package that you might want to put in your environment to see if it's available, to see if we provided it for you. And this new module spider command comes from LMOD. This is a different implementation of an environment module system, and it handles what's called this, which we'll see today as I walk through the system online, and I'll show you. It solves this hierarchy problem, essentially, that you can get into with modules and software in general, right? Software dependencies in general, right? Not every piece of software is accessible from the same, is compatible with all other modules on the system, right? So you can't say load module A and then module B and expect both to work with module C, right? There's a dependency issue that also comes into play when you're managing software environments, right? Not all software that's installed works with, is compatible at the same time, essentially, right? You have to, like, say, unload one set of software to use a different set of software, in some cases, right? So there's a dependency issue and a hierarchy problem here that LMOD does a better job at handling. On Comet, this was all done basically manually, right? Of saying, like, if you load this compiler, this is the versions of MPI you have available to you, for example, for an example. Or if you load this version of MPI, these are the versions of the FFTW library that are available to you, right? So the LMOD system really allows you to handle this in a nicer way. So you don't really have to worry too much about it yourself, but you'll see some of this differences interacting with the module environments. Now, I want to take a step before we look at the module environment on Expanse. I kind of want to take a step back and kind of revisit, like, what the point of what we're talking about here, right? And the thing that you care about at the end of the day is you want to get your software installed, right, on Expanse and get working, right? That's your goal, right? And my goal is to teach you sort of, how to think about doing that, so I don't have to spend too much time helping you do that with you, right? Because I would say, majority of our time is spent helping users install software and satisfy all their dependencies and things like that. So if you can do it yourself, that is, like, good. It's a win for you. It's a win for me, basically, right? And the process of installing your software in a new system is really the software deployment. It's really the process of making your application executable on the target system you want to run, right? And you would say that software is deployed and run within the software environment. So this is how it sort of connects with this idea of what's your software environment, right? Well, for each application, it's probably going to be slightly different, and right, you should we're here. Mostly doing scientific and engineering research, you want to do it in a reproducible way, right? And so, staying organized is key to, doing this, seamlessly. And it's not always the case that's that easy, because systems are different, right? Obviously, over time, computers have changed, and how you get software onto them has changed. Right, it's originally you had to literally plug different wires in to program your system and run a program, right? And we've gotten that was a long time ago, but the three of these systems here probably all ran Fortran, right? So things haven't always changed that much. I'm a Fortran programmer by training, so You know, I could probably run my code on 3 of these systems in some sense, because they all understood Fortran at some points, right? Some version of it, right? But how you actually would deploy that piece of code on each was very different, right? You know, one of them was probably punch cards. The other one was floppy disks. If I'm deploying my, you know, Fortran code to an EC2 instance, it's, you know, just downloading it from GitHub, right? So how you get software onto a system and compiled and run, you know, it's changed over time. That's obvious. But, you know, deploying software on Exceed, you know, as I've mentioned, you know, it's, you know, every system is kind of unique, and you have to really understand the different software environments that are available and what you can use, right? And this is just a simple example, right? This is like one of my own personal codes that I wrote. I'm trying to deploy it on Comet and on Stampede 2. And I just download it from GitHub. There's a make file, and basically it's a very simple code in the sense where it only depends upon a Fortran compiler and an MPI distribution, right? So there's really very little in terms of software dependencies, but you can see here, as soon as I start compiling the code, as long as I just have a Fortran compiler and an MPI, even the output from the compilation is different, right? And I mean, in one case, I'm using, you know, GCC compilers and MVAPICH for my MPI, and on Stampede 2, it's, you know, Intel Fortran compilers and Intel MPI. So yeah, you'd expect kind of like the messaging from the compilers to be different and things like that. But again, it's the point is here, right? It's always a little bespoke, installing even your own software on each system, because the software environment that's available to you is going to be different, right? And it gets more complicated, right? You know, the last example is just Fortran compiler and MPI. You know, some scientific packages that people are using are insanely complicated, and I'm sort of working through some of those right now to support them on Expanse and, you know, get them installed in our module environment so they're easily accessible. So you know, the people who want to use those packages don't have to sort of resolve some crazy set of dependencies like this themselves. Yeah, so it gets complicated. And there's tools, though, to manage these dependencies, right? And, you know, there's some common ones that people use out there to, you know, install software locally on their laptops or desktops versus, you know, what you would use on an HPC system to deploy your software, right? Not everyone is compiling their own software on our systems, right? And that gets to the point, like, not everyone actually needs to use the module environment that we have. And I'll touch on that briefly. But what I want to do is walk through an example of, you know, some of the concepts that, or, you know, basically one of the example problem essentially that, you know, comes up, you know, more often than you would think on our systems. And this is kind of a amalgamation of a couple different emails, but the command that was run is exactly the same. And this user, you know, wrote in and said, "Hey, I'm trying to, do my research, and apparently I need this package, you know, libmpitchdev on Expanse, right? Can you help me install it? Because I tried to install it from the instructions I found online, but it's not working." And, you know, what's the problem here? Like, I don't understand. Like, what's you know, what do I need to do? I need to, like, you know, I have a paper due next week. I don't know, right? So I like this example because it touches on several different, you know, fundamental concepts that I see people get confused on a lot. And that's, I want to walk through like 3 of them that I see here from this kind of example, right? And the first one is the use of this apt command, right? So if you're not familiar with what apt is, it's a command line package tool used to handle, you know, the installation, updating, removal of software packages on Debian-based Linux distributions, right? So one of the fundamental problems is your software environment, right? It depends upon what type of operating system you're using. So the use of this command it doesn't exist on the operating system that you're using. Right? On Comet, Expanse, Bridges 2, Stampede 2, they all run a completely different Linux distribution, which doesn't rely on this apt command line package management tool, right? So the first problem is the user didn't really understand the operating system they were using. If you want to know what operating system your Linux, your cluster that you're running on is using, right? This is kind of a quick command you can look at here. On Expanse, we're running CentOS 8 versus Comet is still running on CentOS 7. But that was like the first fundamental problem here, right? So they're using this package management tool. The second problem was to run apt, if you do use a Debian-based Linux distribution, which a lot of people do, especially like in the data science and machine learning community these days, right? You have to use sudo to use apt, right? So apt is really meant for managing the operating system software, like at the operating system level, right? What's the software that's available system-wide on a given Linux computer, right? And so if we allowed you to run this command, right, even if it was possible to run it, right, it would install this package, and every single user on the system would have to use that lib impatch-dev that you installed. And we're not going to do that, right? So right, every user on these systems has a unique software environment that they need, right? There are certain packages that we will install for users if they request it and it makes sense to put it into the operating system level. Like our HPC systems group will, push out certain packages on Comet and Expanse. On CentOS systems, it would be not apt using it. You would be using Yum to install packages and all the dependencies that are needed on the system there. But it's very few cases. It's usually like simple command line utilities and things that make sense, that there's always only going to be one version. No one's really going to need multiple versions of the same thing. It's not scientific application software. It's something like, I can't think of a good example. I think Screen is one that's been requested, but we have an alternative for that now. And so that was the fundamental problem too in this request, right? So there's no root access for you, right? And the third problem here, which comes to more of the HPC aspect, is this user is trying to install mpitch, which is an MPI library. And so if you're not familiar with MPI, right, this is a library that allows programs to communicate across nodes over a network, right? So talk to basically it's used in distributed memory applications where your application is running across multiple nodes at a given time, right? And the problem here is not that, okay, the user was right. I mean, yeah, they know that they need, say, MPI installed for their application. The problem is things like apt and Yum, they download what are called like pre-compiled binary packages, right? This is the software has already been pre-compiled with a certain set of assumptions, assuming the system and hardware and software configuration that the package will rely on once it's installed, right? And with all of these package managers, HPC is never the default assumption, right? So you're essentially throwing away, like I said, why we're talking about software environments is if you don't install your software correctly, right, you're losing the 0th order optimization, right? So in HPC applications that say need MPI, right, these have to be built with sort of special features for the system that they're running on, right? Like on Expanse, we have several different MPI distributions for you, and they are built with certain special features you would never find in a pre-compiled binary version of MPI, right? Like integration with Slurm, right? As Mahi's examples had, using srun commands instead of MPI run commands. Right, there's obviously if you have a code that can requires, high bandwidth, low latency networking. We have InfiniBand on the system, right? And there's also, options for like GPU awareness for certain MPI distributions, right? That might make sense for you, right? So those were like kind of the three fundamental problems that touched on a lot of things that I see people have problems with when they're trying to set up their software environment, right? So this is maybe it's a bad example, I don't know. But it kind of comes home to like, okay, so if I can't do it like they say how I should do it online, because that's the instructions that they gave me on, this would work maybe on your laptop if you're running like a Debian-based system, but it's not going to work on our systems, right? And so this is where we will jump on to Expanse, and I'll show you around our software environment, but kind of just want to hammer home those points. And what you need to keep in mind when you're navigating around on any HPC system, there's these three levels of system software that's defining your environment at any given time, right? There's the system software that's built and maintained and installed by the HPC systems group. They're using Linux package managers and other tools to manage all of the software sort of that's closest to that's required, basically closest to the hardware, essentially, the operating system, drivers for certain network cards and GPUs and things like that. They're managing that for you, right? Then there's the second layer, which our group manages in HPC. Like, this is the common sort of scientific and engineering application software that you need in libraries, math libraries, things like that, right? And this is what's available in this LMOD-based environment module system, right, which I'll show you. But there's the third layer, which is, okay, there's also the software that you build, install, and maintain yourself in your home directory on Expanse and Comet and other systems, right? And this doesn't necessarily have to use our environment modules, right? We have a lot of people using, Anaconda, for example. So Conda-based installs, or if you're using R, right? It has its own built-in package manager, right? And so while this talk was sort of, to show you around the software environment on Expanse and the module environment, which we'll do here in a second, I want to reiterate the point. That software may not be the software that you need, right? This is just the shared application software that we maintain, right? You might, be more familiar with using Anaconda and doing Conda installs, and that's a completely separate way to manage your software environment, right? Using the module system is the software that we maintain for you, so you're sort of stuck with all of the software that we've installed and the dependencies that are there. And that's built in a certain way, right? If you're doing a Conda environment on Expanse or Comet or any HPC system, right? That's installing, it's kind of like Yum and apt. They're installing pre-compiled binaries that have already been compiled for you by other people and have no reference to Expanse or Comet or any HPC system, right? So you're really limited there to how they've compiled the software. And in most cases, you never want to, there's a few special cases where you would mix, say, the software in the environment modules with a Conda installation, but there's very few cases. So, right, these are kind of independent pre-compiled binary systems for you, right? There's software over here, there's software over there. You don't usually want to mix and match them because they weren't built with the idea that you were going to use them together, right? So this is one of the more common issues I see is people trying to mix software from different software management systems, essentially, and it's it leads to, I think, more confusion than it needs to. That's kind of what this talk is, kind of about. Okay, so we have about 15 minutes left, and so I will jump on Expanse now and show you around. Now that we have sort of touched on some of the concepts that I wanted to talk about. Okay, so let's log into Expanse. And like Comet, you'll see that if we'll talk about the module environment, right? So when you log in, like Comet, there will be a default set of software modules loaded for you, right? So you can see those by typing module list, right? So there's this shared module, the Slurm module is loaded for you. So you can always, find, say, the sbatch command, right? So, by this module being loaded, right, it's telling your software environment where to, your shell program, where to look for the Expanse commands, right, that you want to run, or the Slurm commands that you want to run to, submit jobs to the system. Then the third one here is the CPU -051.4 module, and then there's this fourth default modules. The two really important ones are, I'll focus on here, is the Slurm module and the CPU module, right? So Expanse's login nodes are similar to their compute and shared partition nodes, right? They are AMD EPYC chips, right? And so the hardware architecture is AMD, right? And so, as Mahi, I think, briefly mentioned, is we have different shared application software for the AMD compute nodes, and then we have for the Intel NVIDIA GPU nodes, right? And so the CPU module here is sort of a meta module that allows you access to all of the software that you would use on AMD compute nodes, right? So this is the software that we're providing. I think Mahi and Bob both mentioned we're using SPAC as our package manager for this. I'm not going to touch on the details there, but if you have questions, feel free to ask about what we're doing with SPAC, and if you're interested in that. So the CPU module, and you'll see that there's also the GPU module, right? So those are these meta modules that contain the software for the different architectures on Expanse, right? So that's one thing that's different than Comet, right? If you log into Comet and type module avail, you'll see just a list of software, and it's not clear necessarily which ones are GPU accelerated, right? Or targeting GPU, the GPU nodes on the system, right? Also, I think has been pointed out, right? There's the other glaring module here is the Slurm module, which is kind of annoying personally, I think. But this is, again, a different layer of the software, right? This is coming from the system software, right? The HPC systems group is using a certain type of cluster management system called Bright that helps them manage their software on the system. And the way the Bright does it is they have a module for the scheduler that it's being run. In this case, it's Slurm. So there's a Slurm module. So anytime you want to, anytime you run into a problem with not being able to, say, sbatch submit your job scripts, you probably just forgot that you maybe purged your module environment and forgot to reload the Slurm one. But we load it here by default because we want you to hopefully, just use Slurm right out of the box when you log in if you need to, right? But it's just something to keep in mind. I do it all the time myself still, where I forgot that I purged the module environments, right? And I can't submit jobs with sbatch because it's not in my path, right? So so that's one thing that's different. Right. So there's a module for Slurm, which is something you'll use a lot. And again, there is the CPU and GPU software modules. If you're curious about what the versioning here means for the different meta modules, if you're familiar with SPAC, this is the version of SPAC we're currently on. This will probably be updated in the next, month or two at some point. I think we're kind of waiting for SPAC 17 to come out. Yes. Okay. So those are the 2/3 fundamental modules: the Slurm module, CPU module, and the GPU module. I'll talk about the GPU module in a second. But let's take a quick look at the CPU module environment. Right? So if you type module avail, you'll now see kind of all the packages that are in the module environment that are available to you, right? So, and this comes back to the layout here of the module environment is important, right? This comes back to this hierarchical problem that I was talking about of what software is available and visible to you at any given time. In LMOD is, trying to help you manage the dependencies of the software that's installed on the system for you, right? So at the lower half of the screen here, you see the CM shared references to locations of where these modules are installed. That's again coming from the software, the system software side. Like I said, Slurm is coming from the HPC systems group, and their cluster management tools installs their module files in a particular way, in a particular location. Another one, if you're using Singularity, that's also distributed by the HPC systems group. So that's not in the spec-based modules that we're maintaining. And there's a few other things that are in the meta module is in is managed on the system side essentially. So we sort of created these meta modules to point to the correct spec instance that you're using for your application software essentially in the module environment. So, and at the top level, this is the first view when you load the CPU module, right? So this is the software that's available to you from loading module load CPU 0.15.4, right? And you'll see here there's a few different things. Essentially, the way to think about this level, it's really the compiler, the core compiler level, essentially. This is where we install compiler stacks, software that's compiled with a given compiler for you, right? So this, I'm not saying this correctly. This level is really where we install compilers, essentially, right? So you'll see that there's a bunch of different GCC compilers, there's an Intel compiler, there's the AOCC compiler. There's a few other tools and packages that don't make sense, like living in these other layers of the module environments that are here. But essentially, this is where we install compilers for you and where you'll access different software that's been compiled with those types of compilers, right? So for example, if you want to see the software that's available to you that's been built with GCC 10.2.0, which is important because this is the only GCC compiler we have on the system that supports the Zen 2 architecture at this time. So most of the packages that we're deploying on the system are, or at least right now, many of them are in the GCC 10.2 compiler, or have been built with the 10.2.0 compiler. And so if you do a module load GCC 10.2 and do a module avail again, you'll see it opens a completely different level of the software, right? So it's opened up, now that you're not in the core part of the spec instance, you are at now in the what I would call sort of the GCC 10.2.0 sort of software dependency chain, essentially, right? This is all the software that's been installed to be used with GCC 10.2.0, right? So some of these are complete applications like Beast, right? It's a complete phylogenetic code that you can just run, or what else do we have here? Let's see, Octave, if you're doing some sort of MATLAB type stuff, but in open source. There's not, if there's some good examples. Not yet. So, if you need just GCC 10.2 and FFTW for your code, right? Your FFTW is available here. Now, if you're using an MPI-based code, right, there is another layer that you need to go to, right? So the module system is based on basically there's a core set of compilers, then there's a layer of MPI, and that's sort of the hierarchy that's established. So the main MPI that I use on the system usually is OpenMPI 4 right now. 404 right now. And so if I load that module, it now reveals to you all of the software that's available that works with GCC 10.2 and OpenMPI 404, right? And so you can see here, there's a few pretty popular packages that we have available here. GROMAX is used by a lot of users on the system. LAMPS, this is all sort of molecular dynamic software. And things like ParaView, if you're doing sort of large-scale visualization, it's available. So you can see here that the module environment is different from Comet in the sense that you have to sort of load progressive levels of software layers, essentially, right? So in this hierarchical way to sort of keep your dependencies in check, right? Now, that's kind of a pain if you start from module purge and you just do module avail, right? It's like, okay, well, where is the software? So the way to search for a given package that you might need is with this module spider command that I mentioned. So if I do a module spider, let's see, what's well, I'll just do GROMAX again so we can kind of see. That's not a good example, sorry. Let's do FFTW. I think that's going to be at multiple locations, right? So if I do a module spider FFTW, the spider command, what it does is it returns to you the set of other modules that you have to load to get to a specific version of that package, right? So if you want just for example, like a serialized or maybe shared memory version of FFTW, that's going to live here in the CPU mod. You first load the CPU module, then GCC 10.2, and the FFTW at that level doesn't rely on MPI, right? That's either, I know that's either a serialized version or it's a maybe a shared memory. Maybe it's got OpenMP turned on or something like that, right? If you need an MPI enabled one, well, you have several choices here, right? Probably your most optimal ones are going to be somewhere in this because, right, GC 10.2 is the optimal one for the AMD Zen 2 architecture, and you can choose your flavor of MPI that you want, MVAPH2 or OpenMPI. You can test them out and see which one works best with your code, right? Okay, so that's sort of the CPU module and sort of how the hierarchy works with the LMOD configuration of the module environment on Expanse. And I want to do in the last couple minutes here is just touch on a couple of the things on the GPU side. Okay, so let me see if I can get an interactive node real quick. Well, I won't do that. It'll take too much time. Okay, so I'll just load. So I'll just purge and look at the software environment on the compute node or on the login node. So one thing to keep in mind if you're using MPI is, yeah, you definitely always want to load the Slurm module for the most part because it has it's required for the Slurm integration with MPI on Expanse. So that's one thing to keep in mind. Okay, so let's just list what the packages look like here. Now, the software on the GPU side is a little different right now in the sense that we're mostly relying on the core system compiler for many of the packages that we have installed so far on the GPU nodes. And the reason for this is essentially that the GCC the default compiler, if you log into Expanse, is 831. And this is compatible with the version of CUDA. This is the version of GCC that's compatible with the version of CUDA we have on the system right now. And you can see here at the bottom of the module avail command, CUDA for now is actually coming from the system software side, right? It's in one of these CM shared locations that has to do with the system software. And so if you want to use CUDA and any of the compilers up here, right? So the compilers are coming from this SPAC environment, and it's, you know, it's set up to be compatible with the CUDA that's coming from the system side, this bright managed side. And so if I wanted to, you know, compile something with, you know, GCC 831, there is no compiler module that I would load, right? I would just load, you know, if I wanted to compile something with GCC and CUDA, I would just load the CUDA toolkit here. Right. And so this might look a little funky compared to what we had on the CPU side, but you know, here the default GCC compiler to use with the CUDA toolkit that's installed is just the default GCC compiler on the system, right? So this will probably change, you know, maybe even in the next update of the SPAC installed software, right? You know, at some point, you know, a newer version of GCC will be compatible with the version of CUDA that we install on the system, and then we'll probably just upgrade. You know, that compiler will live in the SPAC installed software module environment. But right now, most of the software relies on that sort of core GCC compiler, right? You can, of course, use the Intel compilers and PGI compilers as well, but that's the one difference between, it's a little bit different than the CPU software stack and the GPU software stack right now. And I think that's pretty much it, what I wanted to touch on with the module environment, and we're pretty much out of time. So maybe we have some time for a few questions or.
So Marty, there's one that is asking about clarifying the issue of mixing modules and conda builds. Why is that a bad idea? And what are some examples where you might do it anyway?
Okay, so yeah, so the main issue with using conda with the software that we've installed through SPAC and a module environment in the module environment is that you can often get turned around and cross, right, all of the packages that come from conda or any sort of package manager were compiled with a certain set of assumptions, right? Where all the modules that are in our SPAC-based install were compiled in with a certain set of assumptions and dependencies there. And mixing and matching just different, I mean, you're essentially mentioning different software environments together, and that can lead to conflicts and problems, and we see that happen quite a bit. So, I mean, one thing right now is we actually have an Anaconda module you'll see in both the CPU and GPU environments, right? So you can install your own mini conda, for example, in your home directory. We also have a centralized Anaconda installation, which has all the default Anaconda packages. So if you just need like default Anaconda, you can use the one that we provide. You're not going to really be able to modify that, but that's okay if you just need some sort of vanilla Anaconda environment. Now, the only case that I see regularly where it makes sense to mix conda installed packages with the module environment on any HPC system is if you're trying to do something with MPI. Right. So the most common mistake I see people who need some sort of MPI based package and they install it through Conda, right? Anaconda brings its own MPI, right? And it's the same problem as the sudo apt-get install libmpitch-dev, right? That MPI has not been compiled to work with the hardware on an HPC system. And what's happening in those cases is if you really do need MPI with your Conda-based installation, it's going to use the Ethernet network. It's going to be very slow. So we can, so for example, like the most common thing I see is, with Python and MPI for Pi, right? So you really have to compile your own MPI for Pi outside of Conda to get this to work with our distributions of MPI. So if you want to use our distributions of MPI that will use the InfiniBand network and you want to use Conda packages that will talk to MPI for Pi, you really have to compile MPI from Pi from source within your Conda environment, but using our MPI distributions, and make sure that Conda doesn't install an MPI distribution. So it gets complicated, right? And so my general rule of thumb is if you're using Anaconda, you don't really need our software modules, because as long as you're sticking to a single node, a single GPU, it'll do everything you need. It's only really when you start talking about doing distributed memory things where it becomes a problem, but there is a hacky solution. So hopefully that answers the question. Okay.
So I think there was one other set of questions earlier, which is more a request for some training on basically configure usage and CMake setup kind of stuff. And that's an interesting suggestion. I think we get enough questions about that we probably should do one.
Like how to use CMake kind of? Is that the...
Like there are, and this is probably more general, it's not an Expanse level training, but it's basically the typical issues we run into with configure, like for example, boost can trip you up, or when you do CMake setup, sometimes it doesn't pick up the just modules is not enough.
Yeah, I mean, for people who don't know what CMake is, yeah, it's essentially a build system that it's there to help you compile certain pieces of software. And one of the common problems is, it has its own way of trying to find where other software is installed on a given system, and it sort of makes a lot of assumptions of where that software is installed. So yeah, it can be a pain. I know. So yeah, I mean, it's a good question, but yeah, it's kind of very usually detailed and specific to just you. I mean, maybe we can talk about this, I mean, when we're doing this talk on, or this sort of half-day training on sort of, really how to compile software and run it in an optimal way on, the AMD system, on the AMD compute nodes in April, and maybe that's something
we can probably talk about it then.
And when we touch on sort of more details of like, all right, if you really are like the type of user who's compiling your software from source, that could, that's might be a good thing to touch on. Because yeah, in our cases, yeah, I don't know how far along CMake is, to assuming it knows where all the spec software is.
So what I've seen is with the SPAC builds, they do reasonably good job of setting up the CMake aspect also.
Yeah.
So it usually gets picked up, but there are always exceptions.
Yeah.
I don't know how to ask a question here.
Actually, we're now running about a little bit over 10 minutes long. If you want to handle this last question,
Sure.
Another question, then we can take another break and maybe reconvene at 10:45.
Yeah, I mean, I could stick around during the break and answer questions if people have questions.
Marty, I think there are some questions.
Okay.
If you want.
Sure.
There's one whether MPI4 is already in our maintained modules or not.
It is not at this time.
Yeah.
So, so we're still working on our deploying our Python stack. But it's going to be there eventually. If you need it right now, you can send us a ticket and we'll help you get it. Either we'll try to get it a version of it installed pretty quickly in through SPAC in the software module environment. It shouldn't be too hard.
I don't see the.
But yeah, it's not there by default yet.
Let me start the chat.
Yeah, but Adrian's question about MPI for Pi. I mean, I brought that up basically because people try to use it in Anaconda environments, and it's when they install it there, it causes this issue of Conda then brings its own MPI into the system, and then you're not using an optimal version of MPI for the hardware that you're on. And, that's kind of the issue. So yeah, I mean, if you don't have to, if you just need MPI for Pi, that's easy to probably get on the system.
Hey guys, let's go ahead and declare the break and then restart back. Right now it's 11:39, almost 11:40. So how about 11:50 or 11:45? What do people think? 10-minute break and then we start back up. That'll put us about 20 minutes behind schedule. But we've got the Q&A at the end, so we can.
Okay, sure.
Okay, or how about we just do 5-minute break? 11:45.
That sounds good.
It's 11:50.
All right, welcome back. So for this section, I'm going to discuss
Nicole?
job. Yes.
I'm looking at your presentation.
Yes.
The split, not the I'm sorry, what was the word looking for? Not the full slide. I'm looking at your notes as well.
Yeah, we're seeing the presentation view,
Thank you.
presenter view.
Yes, thank you.
Nicole, you can do a swap displays.
Shoot. Where's that?
In the presentation view, you can do it.
So once you do the presentation view, and then if it's showing the wrong one, there should be a thing on top there.
Oh, I'm sorry about this.
So you can just share it, and then once it's shared, then you can do the swap.
That one's correct, right? Can you see?
Yes, that looks
Yes.
good.
Looks good.
Okay. Sorry about that.
Thanks, Nicole.
All right, so for this section, I'm going to discuss job charging and allocations management. For those of you coming from Comet, for the most part, this should look fairly simple. However, there are some differences, as Marty and Bob mentioned about about Comet and Expanse resources. So the small nuances are going to be significant in how you're getting charged. So I'll take some time to talk about that. So overall, you should walk into this without any fear because job charging is really simple. As most of you are all aware, all the Exceed resources are allocated as service units. However, not all service units are synonymous across the different type of resources. For example, Expanse and GPU are allocated as separate unique resources. So on Expanse, you're going to be requesting essentially core hours, whereas on Expanse GPU, you're going to be requesting GPU hours. All charges for the jobs when you run them are going to be for the resources that you request, not necessarily how you use those resources. We use trackable resources by CPUs, GPUs, and RAMs. So depending on which resource you are and which you use the most of on that resource, that's what you'll be charged by. And the other thing is the minimum number for any job, regardless of how long it runs, will always be 1 SU. So kind of the overview for charge, the high level, is that the resources you request in your job script multiplied by the job duration in hours, so what you actually run, not what you request, times the charge factor is what you'll be charged. So we've all seen this before, but I did want to bring it up one more time because of this exclusive access. So we have 2 nodes that are exclusive, which means if you request compute or GPU, you're going to receive the entire node. So if you take your batch script that was running on Comet and just put it on Expanse, you're going to be charged significantly more simply because Comet had 24 cores and Expanse has a 120 weight. The other part I wanted to mention in here is to drill down a little bit more on our preempt. So there's a couple benefits to the preempt. So Mahi mentioned that they're discounted. So for 1/8 of the cost, or a portion, you can run the jobs on any free nodes. In addition, you can run it for 7 days. So, however, there are absolutely no refunds for any reason whatsoever. So it's really important that you make sure that you have checkpoint restart on these jobs, or else you're going to lose time. So I'll talk about the specific charging on the different resources. For compute, shared, debug, and preempt, the SUs are evaluated in core hours. On Expanse, Expanse node has 128 cores and 256 gigs of memory. So if you do the math in there, that means that every Expanse SU or core hour is going to be equivalent to approximately 1 core and less than or equal to 2 gigs of memory. So this is a change from Comet, because on Comet, you could get, for 1 core, you would get approximately 5 gigs of memory. One other thing that's really important that Mahi mentioned as well, and I'm going to repeat it because it could hook you up or it could not, is that the default memory, if you don't specifically use the --mem option in your batch script, is you will get 1 gig of memory. The CPU charging will be either cores or memory. So you can request in the shared options, you can request just what you need to allow more people to kind of more efficiently use the nodes. So you can request 1 core, but 5 gigabytes of memory. When you do that, you're going to be charged for the 5 gigabytes of memory. And since it's 5, it's slightly over 3 cores. So you'll be charged for 3 cores in that situation. GPU is very similar in the charging, except for the trackable resources. We have 3 for GPUs. We have the GPUs, the cores, and the memory. So again, from Comet had 4 GPUs, 24 cores for the K80s, 28 cores for the P100s. The GPUs here, for 1 SU, you'll get equivalent to 1 GPU, less than or equal to 10 cores, and less than or equal to 96 gigabytes memories. Again, the same thing applies, that per core you only get 1 gig of memory. So while large memory shared charging is currently, let me reinforce that word, currently, the exact same as a CPU charging. So while the large memory nodes have 128 cores, they have 2 terabytes of memory available to you, which means that 1 large memory core can have up to 16 gigs of memory. But 1 core hour is still considered 1 core and less than or equal to 2 gigabytes of memory. So if you request a large memory node, 1 core and 16 gigs of memory, right now you would be charged for 8 SUs. Another thing, I'm not sure if we mentioned it or not earlier, but on the large memory chart nodes, you cannot use these nodes if you're using less than the max on 1 regular memory node. So you need to request more than 256 gigabytes of memory. So to be able to evaluate where you kind of stand with your job allocations, we have XD usage. but XD usage and the portal, both of those take their data from the XD CDB. Data from both Comet and Expanse only get updated to that database once a day. So if you want to have more current information, you can use the local job script called Expanse Client. To use Expanse Client, you're going to need to load the SDSC module first, and then you can use this tool. Expanse Client replaces what was on Comet, the show accounts and proj details commands. So another really nice feature about Expanse Client is, as I mentioned, the usage for the day is banked only once a day. However, people can be running jobs and submitting jobs during the day, and you won't know where you stand. By using the -V option, it will give you specifics about all in this like used queued. You will see all your usage for jobs that finished within the day, any jobs that are currently running, and any jobs that are currently in the queue. The commands, the Expanse Client will let you see not only, or if you use the users command, will show you all that your personal projects that are available and the overall usage, but you can also use the projects command for it, and it will show you for a certain project, all the users' usage on that project. So in review, this quick and short, all the charges are the same as they are on Comet, except for that we use Trust for this, which means you will be charged for the max usage of either the cores, GPUs, or memory. Multiply that by the time in hours times the charge factor. The default memory per core or GPU in all partitions is always 1 GB. So it's important to take or use the --mem option to specify the amount of memory you need. The minimum charge for any job, regardless of how long you run, even if it runs for a second or two, will be 1 SU. Keep in mind that the nodes on Expanse are different than on Comet. So I strongly recommend that when you're transitioning any of your batch scripts over, you take a good look at them to make sure that you're actually requesting the resources you need so that your jobs don't fail because you don't have enough memory, or that you get overcharged because you're requesting resources that you don't need. If you need any more information, you can check the user guide. And I think that's all I have for you. Any questions? All righty.
Nico, Nico, there's a question on the chat. Maybe you want me to read that to you?
Sure.
Is there a minimum runtime guaranteed for the job to run on the preamp node once it is allocated the resource?
No, there's not. So you can get preempted at any time. So checkpoints restart are really small jobs, is what we'd recommend doing there.
I think there was also a question about automatic requeuing if Slurm kicks your job out. I don't know if that got answered.
So I'm sorry, go on, Mahi.
No, I was saying we're going to check on that. I was actually checking on that.
Yeah, it's a good question. I don't think there's a way, as far as I've seen, I don't think there's a way for that. I mean, what the default is now is your job will be requeued if, for example, your job is running on a node that sort of fails for reasons outside of your job causing the problem, essentially, right? For this sort of node fail status, and your job will be requeued automatically already. But the question here was in the case of if your job, I think called, I mean, well, so yeah, if your job, let's see, what did it say? I think it was if your job actually caused the failure. So if your job causes the failure in Slurm, for example, like one of the most common ones is, you use too much memory. You use more memory. You were about to use more memory than you requested. The Slurm will kill your job and it won't restart that kind of situation. But yeah, I don't know if there's a way to force a retry, because in that case, right, Slurm knows your job, if it just runs again, is going to kill it again, right? You need to adjust how much memory you need for the job. So yeah, it's an interesting question. I don't know.
So
Jacek, one quick question. You mentioned OLCF. Are they also using Slurm, or is it different?
So hey, this is Jacek. So yes, indeed, I think I remember that at the OLCF I believe they use Slurm. I can check on that, and I believe there is also kind of something called like backlog. So basically means you can submit a job, and then yes, it can be killed at any time. But there is an assumption that at least you get like, I don't know, half an hour or something like that. So because if it's less than that, then basically maybe I have to set up check up at every like 5 seconds, right? And that defeats the purpose of the resources. I don't want to have like saving every 5 seconds. So
sure,
I think that would be reasonable to have some like maybe half an hour or something like small amount. But anyway, thanks.
Thanks.
So just to answer a little bit of the question, I mean, there isn't no requeuing. It's a separate job. So if your job starts to run and it's killed, that job is over and it gets charged for the amount of time it runs. If it was requeued, it would then, then there's a billing issue. So
no, there's no problem. No, see, this is no problem with my job being killed and being charged. Let's say I'm running 45 minutes and I'm being charged for whatever that amount is. But but since my job is has built-in checkup and restart, then then it would be nice if the job get automatically requeued. If I set have a flag requeued and then
requeued and rescheduling, right? Because if it's requeued,
okay, whatever,
you're doing the same job, and yeah, we don't do that because the billing issue.
No, I want to do that. I want to do that, right? I want to be able to that it will, like, let's say it gets killed like in the midnight in the midnight, and then like maybe it will start again on 2 a.m. or 4 a.m. right? Otherwise, I have to kind of keep checking all the time. Yeah. Like it's a full-time job to check in.
Right now with the preamp, we don't reschedule the job for you. We don't resubmit the job for you. So that's what. So go ahead, Trevor. Yeah, you have your hand up, and I asked you to. Yeah.
Okay.
Trevor's got his hand up, so he can jump in.
Yeah. So the option to have jobs requeued is under the user's control. The default is to requeue the job, but the user can ask for the job not to be requeued. So that's one thing. The other part about how long the jobs would be able to run before being preempted is a configurable parameter. We currently have it set fairly low. It's only at 2 minutes. You can actually ask Slurm, I wouldn't do this like every minute, what that value is, but it's probably a good idea when you get onto a Slurm system to ask Slurm what is the preempt grace time or the preempt time. I can't remember the exact name of the parameter for that system, and then encode your script sufficiently. You'll get a signal in your batch script that you're going to be preempted, so you have time to respond to that. I think it's a true statement that we haven't had preempt on our Slurm-based systems before, and so I think what I would say is we will work with the people who want to use it to help optimize it. It's likely that when the system is fairly lightly used, i.e. right now, we could make the preempt time quite a bit longer. But when, and leave it that way. And then if the system gets busy, just preempt jobs won't run. And so that's reasonable. So Isaac, I think you might be one of the first people asking this question. So maybe engage with user services and talk to us about what you might like to see us as an optimal time to leave jobs in the queue, and we'll make those choices.
Yeah, I'll be happy to give you some feedback. Also, there's like a quick question, right? So a comment. So let's say I'm starting my job and it runs 5 minutes and get killed. Am I being charged for the full hour?
No, you're charged. You're just basically charged for essentially the CPU seconds, or you're charged by the second, with the case that charging can only be in whole integer values, and so you can't be charged for fractional SUs. So depending on a lot of factors like the size of your job, you're not charged by the hour. We use by the hour to make things simple to explain to people, but the charge could be as little as 1 SU.
That is 1 hour, right?
Folks, I'm going to step in, folks. we still have 3 more talks. Can we move some of this to the Q&A session so we can finish the 3 talks that are remaining in the agenda?
Sure.
I mean, these are great questions, but we do want to make sure we cover all the talks. Thanks, guys. Suba, you ready?
So you can see my slides, right, Mary?
Yes, looks good.
Okay, thanks. Hi, my name is Subha Sivanyanam, and I'm going to talk about the user portal that we have built for Expanse. And in the next 15 minutes or so, I'll describe some of its features and show a brief demo. So the goal of the Expanse user portal is to provide an integrated web-based environment where users perform familiar compute and data operations on Expanse using an easy-to-use interface. The portal is built for launching interactive applications such as MATLAB and RStudio, and also perform some basic system operations like batch job submission and file management. So we have built this portal using an existing NSF-funded project called the Open On Demand, which some of you may have heard of. And we customize the Open On Demand software to work with the Expanse system. And I'll show some, most of these features in the demo, but I just wanted to mention them briefly here. That the portal provides a graphical file management capability where users can view and operate on files either in their home directory or on Lustre Scratch directory. It supports operations such as basic file operations like moving or renaming. You can do some upload of very small files, like less than 2 gigabytes, and also edit files without needing a shell. There is a job composer areas where users can edit and submit batch jobs and also monitor the jobs that are submitted through the portal. We do have some example templates for jobs using MPI and OpenMP, and we'll be adding more. But if there is a need for a specific template or for an application or is being widely used in your research community, please do contact us and we can include that template as well. The portal also, as I mentioned, has the ability to submit interactive jobs. Right now, we support both MATLAB and RStudio jobs, and we are also looking into providing Jupyter notebooks. And any of these interactive jobs, you do not, need to install a local X server, and everything is contained within the web browser. And for users who need an access to terminal, there's an integrated terminal in the portal, and that's very similar to other tools like PuTTY that provide terminal access. If you, Nicole mentioned about the Expanse client. So if you want to see the output of the Expanse client, or rather you want to know information about your allocation or usage, you can do so, in the portal. So now who can use the Expanse portal is any PI or users who have a valid Expanse allocation and have their basic seed credentials set for using Expanse. What that means is your allocation should be approved and your home directory should be created on Expanse before you can use this portal. Although this is obvious, any policy or guidelines set for using Expanse, it could be scheduling policies, so usage, software usage policies, operations, security, all of that is automatically applicable when using the portal. This is a link to our portal. It's just portal.expanse.sdsc.edu, and you can access the portal link even from the Expanse homepage, which is expanse.sdsc.edu, and we have a link to the portal from there. So with that, I'll just show a brief demo, and in the demo, I will show basic file management capability and do an example job submission using both batch as well as an interactive job. So let me just switch to my browser. So as I said, if you go to portal.expanse.sdsc.edu, it will redirect you to the Exceed login page, and you need to sign in using your Exceed portal login or the login that you're using to access Expanse. And upon successful authentication, you'll be redirected to the Expanse Portal webpage. And the features that I mentioned are all up here, like, the file management, job submission, accessing clusters and interactive application. In addition to that, there is a help tab where we have an online user guide that you can look at, and that's a work in progress, and we will be updating that as we add more features to the Expanse Portal. So under the files, you can access both your home directory as well as the Lustre Scratch directory. This is my home directory. And as I mentioned, you can do, like, basically you can view a file, you can edit, you can rename, you can download a copy of the file, you can create new files and directories, and you can do all the basic file management operations here. So if you want to edit it, I can just pick a file and it opens a text editor, which you can customize. You can make whatever changes you want. For example, I can just print a date here. And if you save it, it saves it to the same location on Expanse file system. So, and you can use the same job script, right? If you have written a job script down, you can use the same job script using the portal to submit a batch job. So under the Jobs tab, you can view any jobs that are being that you've submitted using the portal, or you can create a new job or use an existing job from your home directory or other allocations that you may have, like the Scratch file system. So here under the new job, you can you can create a new job using one of our existing templates. And currently we have like a basic hello world template that you can copy and modify. We have an MPI and we have an OpenMP template. And just for this demo, I'll be using this hello world. The way we do it is when you click on the create a new job, it copies the template and allows you to be able to edit it. So for here, there is no account specified, and that's something that you need to specify to run a job on Expanse. And you can do that in two ways. One is we have a job options area where you can go in and specify the account that your accounts. And I know my account is use 300. And if you don't know your account, I'll also show you how to get that information in a bit. So and once you save it, you can see that the account is now set. And the other way you can edit it is there is an open edit button here, which you can open it and you can edit the badge submission script according to your requirements. So here I'm just going to remove the date. Since I already have an account, that will be automatically populated with the script. I'm just saving it, and now it should be updated in a second. Yeah, it got updated. And now I can submit this job. And once a job is successfully submitted, you can, this is a pretty short job, it may run really fast now, but you can view the status of the job over here. It's queued right now. Once it starts running, the status will be updated and it's completed. You can also view that here. Then this is just the information that you would get out of, for example, if you're done on the terminal, if you do an S control show job, it's something similar that is getting displayed over here. So once the job is completed, so I have a completed job here, the same hello world. Oh, then actually this job is completed too. You can view the output over here, and the output of this is just a simple hello world. But you can either view, and you can also be able to download your files. So, in case if you don't know your account information and you want to look your project, whatever your project account, if you have multiple projects and you want to see all of them, and you can go to the allocation and usage link, and that shows you the project name here, which you can use in your job script. It also shows, and this is exactly the output of your Expanse-client user. And we'll be adding soon an option to add Expanse-client project. And also we will be expanding this part, include more job management and usage monitoring capabilities. So as I mentioned, you can also submit some interactive applications. So here we support both MATLAB and RStudio, and I will do a quick demo with the MATLAB. So in this interface, you can submit a single node job, but you can decide on your partition if you want to run on computer shared. You can decide the number of hours that your job would need. Specify the account. You can, and if you want to receive an email when the session starts, you can choose this option. And also choose a working directory. Where do you want to run this job, from the scratch or the home? Decide on the number of cores and the memory. And for here, I'm just going to leave all of these options as is and then launch the interactive job. So so right now it's queued, and once the node becomes available, this box will become active. And actually it's running right now. And since I asked for compute, it's running on all 128 cores. And I just want to point out this view only link. For example, say if you are debugging this with some colleague or your student, and you want them to be able to see what you're doing, you can share this. Share this link with them, and they'll be able to monitor what you're doing when you launch this MATLAB. And again, that is only active as long as the job is running on the node. So now I'm going to launch the MATLAB just to show a quick demo to run the MATLAB. So this is so now it's running on the node, and I'm going to just maybe create a 5x5 matrix and then plot it just to demo that you can run interactive job using the portal, using MATLAB. And similarly, you can do the same thing for RStudio. And if you have multiple interactive applications, they'll all be listed here. You can go see all the sessions that was either completed, and I think it will be listed for 6 days after it's completed. And just for debugging purpose, if in case anything goes wrong with that particular job. But in general, if you have multiple sessions, it'll all be listed under this My Interactive sessions. So other than this, we have the integrated terminal here, and which is, I think everybody's familiar with that, and it just gives you a terminal access that you can use from your browser. So with that's sort of my end of my talk here, but I'm happy to take any questions.
I think the chat's been handled pretty well. So if there aren't any other questions,
Okay.
I guess that's it. That was great, Suba. Thank you.
Okay, thank you, Jeff.
Okay, I'll just get my screen set up to share. Can you see my window?
Yes.
And my presentation properly?
That looks good.
I get this out of the way. Is the screen share icon from Zoom showing up in the window for you guys? All right, so my name is Mary Thomas, and I'm going to talk about interactive computing on Expanse. So in relationship to the talk that Bob gave this morning, we're just going to zero in on interactive computing. So we'll talk about that and the types of interactive computing currently available on Expanse, and then how to access interactive nodes and run some applications, including Jupyter notebooks. So what's interactive?
And Mary, I'm sorry to interrupt. The bar for the Zoom toolbar is still obscuring the title of the slide. I think if you drag it a little higher, that might solve the problem. Or
yeah, it's not going to let me. I'll just put it down on the lower left. It's not letting me move it. It's on both of my screens. Is that better?
Yeah, that's better.
Okay. All right. So now, all right. So thanks, Jeff. So what's interactive computing? It depends on your perspective. In computer science, it's really basically any application or code that you're running where you give some input while the code is running. And then for high performance computing, it's a little bit different because interactive implies real-time user inputs, but traditionally high performance computing is associated with jobs that run on the queue, and they run basically without your doing live input. So you submit your job to that Slurm queue, and then later on the job is done, it runs, and you get back your result. So how do we do interactive computing on HPC systems, and why? There are still reasons to want to do things interactively. For example, if you have large data, you'll probably want to run your visualization on an HPC node so you can move your data in and out because it won't even fit on your laptop. Jupyter notebooks are another common example. The MATLAB and RStudio that Suba just showed you, those are interactive. So we want to be able to have different, these are the different scenarios that are involved, like Jupyter notebooks. Most of you are familiar with those, I assume. And Parallel MATLAB, which is also available. Jupyter, and then also ParaView is another example of a HPC application that can run in parallel, and it's interactive. So there's a lot more. That just is the beginning of some of the interactive ones. For example, if you want to do compute steering. So how to get a compute node on Expanse. It's very similar to Comet. So that should look familiar to you. If you've been using Comet, you'll get the same response. So you want to make sure you define a partition. We're suggesting that you use shared partitions for CPU and GPU, and that you also have to include the account number. So the commands are pretty similar for CPU and GPU, with the exception on GPU. You have to tell it how many that you want. And remember, if you're not going to use the whole node, use shared, and remember to include your account number. So that's really what you want to do on that interactive node is up to you. You could be running just your compiler because it takes a lot of time. And if you had your own node and not competing with people on a login node, I'm not going to do a lot of examples, but if you've been doing interactive computing, then you'll know what you want to do on this. And if not, you can look into scenarios where you might need to interact with your code. The most common one these days is Jupyter services. So for the remainder of my talk, I'm going to focus on that because they're so popular and they're used more and more in tutorials for everything from how to write Python code and other languages to machine learning and visualization and things in between. So there are three common Jupyter services. And Jupyter is open source. It's been around for a while now. And when you talk about the thingies that you run, they call them services. So that would be a notebook, Jupyter Lab, or Jupyter Hub, which is multi-user. When you run a notebook or you run a Jupyter Lab, that's a single user. It'll launch and run as you in your environment. Jupyter Hub is almost like a portal to only Jupyter notebooks. So to run them on your laptop, you're going to install that software called Anaconda. On HPC systems, you can install Anaconda, but it's big, and you don't really need all of that typically if you're running in a single user environment. And as Marty already mentioned, we're working on Anaconda installations that work well in the large HPC complex environment. So for now, I would recommend you install Miniconda, and we've got tutorial information. If you go to hpctraining.sdsc.edu, you'll find a tutorial on the notebooks, and we have specific instructions that work on Expanse. So using it on your laptop, just to give you an idea if you've not done much of it, when you install Anaconda, you get a lot of tools. You get Jupyter Lab, you get Jupyter Notebook, you get Spider, which is different than Module Spider, you get RStudio, Orange, GlueViz, and other applications. You don't need all those necessarily on the HPC systems, but you get the Jupyter Lab and the Jupyter Notebook are two common uses of Anaconda, of Jupyter services on HPC systems. And when you're running on your laptop, you always get some output in a shell window. So getting down to HPC systems, it's going to be different. And we're going to use something called the Miniconda environment, which is a mini Anaconda. It runs on Windows, Mac, and Linux. And it's a lot less overhead than Anaconda. So for Python, it's created for Python programs mainly, although they do have kernels you can add for different languages, even a Fortran kernel. But it runs differently than things that are a Python kernel. So you can download it from conda.io, just go there. Their documentation is really good. And what's in our tutorial is just specifically how to do a simple installation on Expanse. So go to the notebook tutorial for that. And when you're ready to use it, you want to, when you do install it, this is the little caveat, is it will put some code into your .bashrc or .bash_profile file. And that means every time you log in, Conda will be turned on and activated and impact your current environment. And if you don't need or want Conda, and Marty showed you an example in the chat about one of the issues of mixing environments, you want to make sure to not have that on unless you explicitly want it, because activating Conda will change your environment. So what we recommend you do is just take all that out, and I just put it in a text file and then run these 2 commands, and you'll be in the Conda environment, and you'll know you're there because you'll have a prefix to your login prompt that tells you which environment, and by default you load in with the base environment. A nice little cheat sheet is in this talk as well, a link to that. So Conda environments, you load it in 2 ways, as I said, at login from your bash file, for example, or command line. So reiterating that, I suggest that you use a text file, store these commands, run them, and then make sure you know what environment you are. So I don't have time to go and do live demos, unfortunately, but the code here is exactly what I got today, this morning, as I was running it. So note, you'll get a different prefix. You can make custom environments, and the prefix then will reflect which one that you're in. So to create a virtual environment, Conda create with the name of some example, and then to see which ones you've got, you can do a list. And then if you want to activate something, you would source and activate that. Or you can use a source activate example. So here's a real live example. I'm listing my environment and the packages that are in it. This is a very long list, and I just snipped out the middle lines, but I've built a lot of stuff into my default Conda environment. And I'm going to make here an example of a demo environment and get the package all built. It takes a couple minutes. Once it's done, I get instructions on how to activate and how to deactivate. So to show that they work, I activated it. Now notice this base here, once I activate it, I get into the demo environment. So then if I look and see if I have anything in the environment, I don't. So I install NumPy, which takes about 5 minutes. When it's done and I do a list, I have a lot more packages in my demo environment. And again, this was only about 15 lines long, so I did a snip just for the example. It's not nearly as complex as my base. And when I want to get out of the demo environment, like for the BioConda, that's one of the chat questions was about, you would end up with some different prefix. And when you want to get out of it, you just deactivate. So then I was changed from the demo environment to the base. And when I want to get out of Conda completely, I go back into the regular login prompt. So I'm not in any kind of Conda environment. And this is where Marty was really bringing up an important point, is you have to know which environment of the software stack you're working with. In order to make things run, I still am going to need some baseline modules, like if I want to do something like run a Jupyter notebook using a code system I'll show you soon. I still need to have the SDSC module loaded. I still need to have Slurm loaded. So there are some basic things, and then you start adding in the Conda environment for doing, in this case, Jupyter notebooks. And as Marty pointed out, it's not very simple, but once you get control of it, you develop systems and it becomes a lot more straightforward for you. All right, so if we want to run Jupyter services, you have to install the notebook, you have to install Jupyter Lab. It's really pretty straightforward. And once it's done, it just might take a few minutes. There may be some hidden dependencies. For example, when you launch a notebook, you might need NumPy and you might not have installed it, so you'll be fiddling with that as well. And it can take a while to install these, but once you have them, then you can run a notebook. A lot of people like to run them from the command line, but now we're going to get to one of the key points of this project is we've learned that there's some key vulnerabilities in a lot of the Jupyter services. They tend to run on login nodes, and or if you run it from the command line, you don't have a secure server. So there's two issues. So for example, we have a policy that portals, Jupyter Hub, and other services like that can't be mounted directly to the login disk. They must be on an external VM or come from some external project because they use root in vulnerable ways. And when you launch a Jupyter Lab, if you launch anything like that on the command line, we'll kill those jobs. And also when you launch just from the command line, in general, these are HTTP, they're not secure. So we've been working on a project to add security to the Jupyter Notebook. And I'll say this several times, when you launch a Jupyter Notebook and you put this URL into your browser, that's like an open password to your account. I can see everything in my account, and including the notebooks that I want to run. So you need to be a little more cautious when you're running notebooks. So there's different ways you can connect and run a notebook. You can do it by default from the command line, and it will be insecure, and your account will be vulnerable. You can connect over SSH using tunneling. I'll describe that in a moment. And that's more secure, but it's not convenient. And it turns out to not be really stable. These SSH connections can die out. And then we've developed a service called the reverse proxy service, which gives you a secure and stable HTTPS or sort of secure encrypted communication channel between your laptop where you're running it, your browser, and the remote service running on a compute node. And so we allow Jupyter services to be run on interactive nodes, compute nodes, and GPU nodes. So the regular connection as Jupyter is defined in an HPC world is you're on your laptop and you SSH over, you get a terminal window, you launch a Jupyter notebook using the Jupyter command, and over time you get that notebook launched. Usually the default port is 8888, and over HTTP you get a connection to your browser. Even though you're connected using a secure encrypted SSH connection between your laptop terminal and the remote computer, you're still just getting an open, insecure, unencrypted HTTP connection. So somebody can sniff that connection, grab your URL, and then log in, hack in, and act as you, and perhaps do malicious things that mostly will affect your account. We have accounts pretty well sandboxed. So this is what we have a problem with HTTP connections like this. So you can do secure connection where you do an SSH over to the machine, and on the machine you launch the Jupyter Notebook, but you do a port-to-port connection between a port that you've opened on your machine and a port that you open on the node. And indeed, this connection is secure, and you can use SSH tunnel, but it's not very, like I said, stable. And it's a little inconvenient. You have to make sure you pick port numbers that are supported and not already in use. And we do have some notes on setting up SSH tunneling. What we came up with is a reverse proxy service. So when you log in to, this one is an example on Comet, but Expanse, and you run our start Jupyter script, you'll make a connection to submitting a job to the batch script, and the script will build a request to get a URL from our reverse proxy service. This is all behind the firewall. And when the Slurm system allocates you a compute node, then this is internally over the internal network. But what you get back is that compute node will connect back to the reverse proxy service, and your HTTPS connection then will connect you on your browser through that service to your compute node, and you'll see all your notebooks, but this is secure and encrypted. So it's simple, you don't have to tunnel, and it produces these secure URLs. And to use it is fairly straightforward. You log on to Expanse, you clone the repo, check that you have the right software environment, all the Python packages that you might need for your particular notebook. And we have some installation instructions to help you get Conda going. And then you can start running, and I'll show you an example in the next slide. We do have a repo with a bunch of example notebooks that run on Expanse, so you can grab those just to test and see if the system's working. So here's an example of just the installation. You clone the repo, and then when you go into the reverse proxy directory, you'll see the start Jupyter script. That's what starts everything running. And then we have a couple of the directories actually have notebooks in them that will get picked by the start Jupyter script to submit a job to the batch queue. We've pre-built these notebooks. You can modify them. I mean, the batch scripts that submit requests to get a node to run a notebook on them. We've pre-built those, and you can modify them and then pass them as an argument to the start Jupyter script. There's a couple more files to show you. There is configurations that this one will be, you can use it to configure different machines. And then we have some basic library functions. To start it, pretty straightforward. Here's the start Jupyter script with the arguments. You can define the partition, the directory, the account, the batch script, how long you want the notebook to run, and then get extra information. The account, we have to have that, and minimally you have to have the account, and you have to define whether it's a notebook or a Jupyter Lab. And we do have CPU notebooks running now, and GPU notebooks are in beta testing right now, along with machine learning notebooks. So real world example, start Jupyter. I'm in the base, I've loaded my Conda environment. I do start Jupyter-B, and I'm going to use the Slurm for Jupyter Lab. My notebook is here. What you get back is a crazy wonky looking URL, but this is to make the URL tokens unique. And one thing, a security note is this URL is a password to your account. So don't share it and don't leave it open if you have to walk away from your laptop and you're in a public environment. And it's going to use the default partition in this example and run for 30 minutes. So this is an example behind here to let you know that you can look in these scripts and see what they do, and copy them, edit them, and make your own version. So what you do is you grab this URL, paste it into your browser, and then wait until it does get launched. And what's going to affect how long you wait is really how busy the queuing system is. So on the command line, you can just run, a check and keep looking to see if you have a job in the queue and is it pending or is it running. And then once it starts running, here our Jupyter Lab has run. You'll notice it's got a secure icon there. So it's HTTPS. And I can look at different notebooks, or I could look in a terminal, all the services that come with Jupyter Lab. When you're done, make sure you quit the Jupyter Lab or the notebook to kill the service running on the remote cluster. If you just log out, the remote service is still running, and it will run until it times out or you kill it. So if you don't want anybody working with this, just quit the notebook or the Jupyter Lab. You can, as Suba showed you on the portal, there's a lot of capability. If you're logged into the portal and you want to just run from there, you can launch, at the moment, you can launch a terminal and do, this is a regular terminal, and you can go right in and use your reverse proxy services. But we are working with the OOD people to make it, the Jupyter reverse proxy service, available through the portal. So that's it. So we have, the reverse proxy service runs on all SDSC systems. There is a server available. We're trying to design this so it can run on any system. And if you want to try and install it, it's called the Satellite Expanse. And you could try and install your own version of an RPS and run your code, not on our systems, but on your own. And so we are working, like I said, on GPU Jupyter services. They're in beta testing now, and I think in the next week or two they'll be in production. And we're working on machine learning notebooks, PyTorch, and other examples, simple machine learning examples. And we're gonna, like I said, we're working and talking with Suba and her team to integrate this in, so it'll just be another interactive service that you can use, and it'll be easier for you to access your notebooks. And then the global system-wide installation that Marty mentioned, there is a global one. It's in early testing, and all the module environments need to be tested, and so we're working on that. So at some point you will never have to install Conda or anything if you want to do like the default supported Jupyter Notebook, Jupyter services on your own. And I think with that, thank you for your time. There's a couple of references, and that's it. Thank you. Any questions?
Yeah, Mary,
Adrian, go ahead.
Yeah, there was one question on how would you install a Jupyter Notebook or Lab extension in kind of your setup?
What
if
extension?
you're using it. I mean, I think they're probably talking about, you know, if it's like not Python or something like that. I mean, I assume you would just do that through, if you're using Conda, you would install the extensions that way.
Yeah, you can. That's a bit tricky. If you go out of the default Python environment and you try to go to a Java environment or a C or even Fortran, it's very tricky to do that. If you're just installing Python packages, everything should work fine. But I couldn't answer that at the moment. We got a Fortran environment to work, but it was not very, I mean, we even got a Unix environment to work, but it was not very, what's the word, smooth. So we'd have to look at your particular case to what you're trying to do. I see people asking about MPI. Oh, can I show my last slide with the references? Sure. You don't necessarily use MPI with Jupyter Notebooks. There's Dask, D-A-S-K, and Apache Spark as well for parallel computing. As far as I know, there's not an MPI yet. It's going to be based on right now parallel Python, but I'm looking into that. Yeah, and I'll put up the last slide. Oh, there's a copy of my talk on the GitHub repo with this. The slide is there.
And we only have 15 minutes left.
Yeah, okay,
so
sorry
let's
about that.
Move on to,
Okay,
I think Nicole's going to talk about data transfer mechanisms next.
I am. Did I get the right screen this time?
Yes.
Yeah.
Oh, good. Okay, so for our final section of the day, I'm going to do a really quick review of the storage that we have available. We've already talked about it, but because of the new policies, it's going to kind of reinforce why it's so important to have a data plan in place to make sure that you keep all of those important files and outputs. And I'll show you some tools on how to best take care of that. So as a quick review, you have the home file system. We have the global parallel file system. Things I wanted to note is that the path to the parallel file systems is slightly different on Expanse than it was on Comet. Before on Comet, it was /Oasis something. On Expanse, it's /Expanse Lustre. On the Lustre file systems, there are absolutely no backups. So it's the purge policies are even more significant at that point. So again, for the Scratch directories, these files are meant to be there less than 30 days. So the files that should be there are files that are actively being used for active jobs. The files will be purged 90 days, 3 months, not 30 days. 90 days after its creation date. So touching the files won't help you out in this instance, as Mahi mentioned. At the point where these files are no longer actively used for running jobs, you can move them over into the project file space. where you're doing maybe more data analysis and stuff. In the project file space, this is allocated resource. So through Exceed, you can request this time. By default, everyone gets 500 gigs. If you need more, you can request a supplement or actually put it into your initial request to have more space there. At the end of your project, you'll have 90 days to clear out that space or get a renewal to the project. So Expanse users, again, as Mahi noted, should avoid doing any compute or IO intensive tasks on the login nodes. So this includes moving any large amounts of data. So SDSC provides for you 4 data mover nodes. The data mover nodes are load balanced in round robin fashion. You can access them by SSHing into them directly. The path is, or the name is there, oasis-dm-interactive.sdsc.edu. One thing to note that when you log into the data mover nodes, the default home directory will be your Comet home directory. So you're going to need to navigate to the Expanse directories with a /expanse. Due to the automated purge policy, we recommend that having a data plan, you get that in kind of in your workflow so that it's always there and that you're never surprised when this comes up. As Mahi mentioned, we will send out a global notice to all users when we run it for the first time, but after that, it's going to run every day, and any files older or out of the quota that is set for that specific file system will be deleted. So the tools you choose, not only is it important to choose from where you're moving your files, but it's also the tools you choose to move them is going to depend on the size of the files and the number of files you need to move. So for smaller files, you can use SCP and rsync, but for larger data transfers and large data sets, the Globus toolkit, and then I'm going to kind of introduce a couple other tools that you could use as well. So for small files, and we consider small files anything less than 2 gigabytes of data, you can use SCP or Secure Copy Protocol. It's a utility for securely transferring files from one computer to another. You can do it from a local to a remote or between 2 remote systems. You can also use SFTP, which is Secure File Transfer Protocol. This utility has a bit more functionalities that allow you for secure file access, transfer, and management. Another option, I saw this in the chat, was someone was using the rsync. If you want to maintain two file structures on 2 separate systems, you can use the rsync command. This is nice because it will only update files or directories that have changed since you last did your rsync. The other thing I wanted to mention about rsync is rsync also can preserve the timestamps on the files. So this might be really important, again, if you're maintaining 2 separate locations that you want to know when the file was created or last touched. So the next 3 data transfer techniques are going to rely on the Globus toolkit. The Globus GSI is no OpenSSH implementation of OpenSSH. So the tools you can use are GSI SCP and GSI FTP. These are similar to the OpenSSH SCP and SFTP. You can use these tools if you log into the single sign-on hub. One important thing is to use any of the Globus tools, you need to have an active Exceed allocation. So when one of the times this might be a concern is if your allocation ends, you still have 3 months to move your data out of the project space, but you don't have an Exceed active allocation. So you just need to send a help ticket into us at either at help@exceed.org or consult@sdsc.edu, and we can get you set up so you can use the Globus tools again. If you are more comfortable with a GUI interface, you can use the Globus GUI. The path to that is www.globus.org. We have endpoints for both Exceed and Comet, Exceed #Comet. Again, when you log into Comet, by default, you won't be in the home directory. You'll have to use the /expanse to get to those, the Expanse files directories. Finally, my third tool for Globus is Globus URL copy. And this tool is recommended for large files or large number of files. And when we say large number of files, we mean large individual files that are at least significant in size. If you're moving a lot of really, really small files, it will actually cost you more to use grid FTP because of the overhead costs of running it. So if you have a lot of very small files, we suggest that you tar it up and send it as one individual file versus several small ones. Before you can use the URL copy, you're first going to have to load the Globus module. Next, you need to make sure that you have an active proxy certificate. You can check if you have one by using the grid-proxy-info command. If you do not have a grid proxy that will be long enough to handle your file transfer, you can create a new one using my proxy logon command. One thing is the certificates are usually active for, I think, 12 hours. So if you're not going to have enough time, we suggest you just use create a new one. So I'll briefly mention two other tools that are available on the data mover nodes. You can use IBM Aspera. This will help you with big data transfers and syncing. You can also use this for automation. So where I mentioned before, if you plan it in your workflow and if you put it in your scripts, the data backups, you're more likely not to be unpleasantly surprised when your data is not there. Also, with the tools now going into the cloud, you can use the AWS command line interface. This is an open source tool that allows you to do commands in your command shell. So you can use any Linux shell or you can use the Windows command line. There's more information on this. I'm gonna leave this kind of high level because I can't go into detail with this and allow some additional time for questions since we've got about 10 minutes left. Actually one more really, really important thing. So the Lustre file system is gonna go away on July 31st. This doesn't mean that the system will retire, then there's still time to move your data. The file system will go away on July 31st. So it's really important to start thinking now of how you're going to get your data off that system and into Expanse. I don't know if this was mentioned before, but we are not mounting any of the file systems from Comet on Expanse, and we're not going to be moving any data. So this is a really good time for people to go through and identify which data is not needed. If the data is archival, it should go into a more persistent storage. And if it's going to be used for active runs or processing or analysis, then it can stay on the systems. That's all I have. Do we have any questions?
I think, Nicole, one thing that came up, but I don't know if you mentioned it, but the question was, where is the purge policy applied? And I think it came across definitely that the Expanse Lustre Scratch has the 90-day policy on creation, but did you also mention the policy on Lustre projects?
So Lustre projects is 90 days from the end of the allocation.
So yeah, so basically, if you don't renew your allocation on Expanse, we will likely clear it out at the 90-day mark. I don't think it's implemented yet, but that's the plan, right?
Yes, it's not implemented yet, and I will post the. But I assume, well.
I mean, all the allocations are new, so everybody's got a year basically. So.
For Scratch Space, we're coming on to when our first purge will come into play. Because it's
but for the project space, I think, right?
Oh yeah, for project space, no, you have some time. I'm gonna copy and paste the Data Oasis path again.
So So one last question here was, what are the best practices to enable a backup of your Expanse Lustre project space?
So when you say best, which tools to use or how often to do it, generally, again, I want to mention that the project space is not backed up locally. So it should be an ongoing effort to protect your data, to put it to more archival storage on a regular basis.
So yeah, it would be something on your local home institution or your lab resources or something like that. But you need to make an offsite copy so that you're not dependent with the sole copy sitting on a active file system.
Yeah. If there's no other specific questions about that last thing, we can kind of open it up to any other questions that kind of came up during this day. We've got about 5 more minutes according to my clock.
I'm showing 1 more minute, but we're still flexible and we'll make sure the recording is available. But yeah, are there any other questions for any of this event? Thanks everyone for hanging in there so long. Okay, then as I mentioned in the chat itself has been very helpful, and thanks very much to all the folks who were stepping in to answer the questions. So I'll make that chat available online as well. So we'll get the recording and the chat up as soon as possible within the next day or 2, hopefully, depending on how quickly Zoom can do the transcription. So thanks again to all the presenters. With that, I will end the recording and